This is the Milky Way, our home. A sprawling city of hundreds of billions of stars, a swirling masterpiece of cosmic light and shadow that has captivated humanity since we first looked toward the heavens. It's a vision of sublime beauty and unimaginable scale, a glowing river of light painting a stripe across our night sky. We see its graceful spiral arms, its bright, bustling core, its dark lanes of interstellar dust. We feel a sense of place, of belonging to this magnificent structure. But everything you see here, everything we've ever called our galaxy, is a lie. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Or rather, it's just a tiny fraction of the truth. A beautiful, glittering illusion. We are living inside an invisible giant, a ghostly structure of mysterious dark matter so enormous and so massive that the entire, familiar galaxy we see is nothing more than a speck of light at its heart. The home we thought we knew is just the brightly lit foyer of a cosmic mansion that stretches for over 1,000,000 light-years in every direction. For decades, scientists have been chasing the ghost in our own machine, trying to map the true boundaries of our galactic home. And what they're finding is redefining our place in the universe, revealing a structure so vast it forces us to ask a profound question. What is the Milky Way, really? The galaxy we thought we knew. Before we venture into the great, invisible unknown, let's take a moment to appreciate the home we thought we knew. The Milky Way as we see it, the part that shines, is a marvel of cosmic architecture. It's a barred spiral galaxy, a colossal, spinning pinwheel of stars, gas, and dust. From one edge of its visible disk to the other, it measures roughly 100,000 light-years. If you could shrink our solar system down to the size of a coffee cup, the visible Milky Way would be the size of the entire North American continent. And what a complex structure it is! At its heart lies the galactic bulge, a dense, tightly packed sphere of older, yellower stars. And at the very center of that bulge, hidden by thick curtains of gas and dust, lurks Sagittarius A*, a supermassive object with the mass of over 4 million suns. For decades, we've believed this to be a supermassive black hole, and that's still the leading theory. But some recent, mind-bending research in 2026 suggests it could even be a dense core of a strange type of fermionic dark matter. Whatever it is, its immense gravity is the anchor point around which our entire galaxy pirouettes in a slow, majestic dance, completing a single revolution roughly once every 220 to 250 million years. Extending from this central region are the galaxy's famous spiral arms, great curving lanes of star formation that give the Milky Way its iconic pinwheel shape. These arms aren't solid structures, but rather density waves. Think of them as cosmic traffic jams where gas and dust get compressed, triggering furious bursts of star birth. This is where we find the youngest, hottest, and brightest blue stars, illuminating the arms like strings of brilliant holiday lights. Dark, weaving lanes of interstellar dust trace their contours, obscuring the light from behind and creating that patchy, mottled look we see when we look up at the Milky Way. And where are we in this grand structure? We're not in the chaotic, radiation-blasted center, nor are we on the lonely outskirts. Our solar system resides in a relatively quiet, suburban neighborhood known as the Orion Arm, or the Orion Spur. It's a smaller, minor arm nestled between the larger Sagittarius and Perseus arms. We sit about 26,000 light-years away from the galactic core, far enough to be safe, but close enough to enjoy a rich, starry sky. This is the picture of the Milky Way we've built over centuries. A beautiful, self-contained island of stars, 100,000 light-years across, adrift in the vast, dark ocean of space. It feels like home. And for a long time, we thought that was the end of the story. But in science, the biggest revolutions often begin not with a bang, but with a small, nagging problem. A single loose thread that, when pulled, unravels everything. And the first thread in this story was pulled not in our own backyard, but in a distant cluster of galaxies, by a brilliant and notoriously cranky astronomer who saw something that just shouldn't be there. The first clue: the runaway galaxies. The year was 1933. The astronomer was Fritz Zwicky, a Swiss scientist at Caltech. Zwicky was a man famous for two things: his abrasive personality and his brilliant, far ahead of his time ideas. He was studying the Coma cluster, a massive swarm of over 1,000 galaxies about 320 million light-years away. Using the telescopes of his day, Zwicky measured the speeds of the individual galaxies as they danced around their common center of gravity. And what he found was deeply troubling. The galaxies were moving at tremendous speeds, way faster than they should have been. He did a quick calculation. First, he estimated the total mass of the cluster by adding up all the light from its galaxies. More light means more stars, which means more mass. This gave him the total visible matter. Then, he used the laws of gravity to figure out how much mass was needed to keep those fast-moving galaxies from flying apart. The cluster had to have enough gravitational glue to hold itself together. The two numbers didn't match. They weren't even in the same ballpark. Zwicky's calculations showed that the cluster needed a staggering amount of extra mass, perhaps 10 to 100 times more than he could see, to explain the frenetic speeds of its galaxies. It was like watching a group of kids on a merry-go-round spinning at the speed of a fighter jet, yet somehow, they weren't being flung off. There had to be some invisible mass holding everything in place. Zwicky, in a flash of insight, proposed a radical solution. The universe was filled with a mysterious, unseen substance he called Dunkel Materie, German for dark matter. It was a revolutionary idea, but the astronomical community largely ignored it. Zwicky's reputation as a difficult character didn't help, and his data was still early and imprecise. For nearly 40 years, the idea of dark matter just simmered on the back burner. But the mystery didn't go away, and in the 1970s, the case was blown wide open by the meticulous work of an American astronomer named Vera Rubin. Vera Rubin wasn't studying vast galaxy clusters. She was looking much closer to home, at individual spiral galaxies, a lot like our own Milky Way. She and her collaborator Kent Ford were using a new, highly sensitive spectrograph to do something with unprecedented precision: measure the rotation speed of stars within a galaxy. According to everything we knew from Newton and Kepler, this should have been simple. Just like in our solar system, where Mercury zips around the Sun much faster than distant Neptune, stars near a galaxy's bright, massive center should move quickly. As you moved further out toward the dim edges, the stars should slow down, because there's less and less visible matter to hold them in orbit. If you plotted this on a graph, the rotation curve should rise and then fall off. But that is not what Vera Rubin found. Night after night, Rubin and Ford pointed their telescope at the Andromeda galaxy, our closest spiral neighbor. When they plotted the data, the graph was shocking. The rotation curve didn't fall, it went flat. The stars at the very edge of Andromeda, far from the bright core, were orbiting at the same blistering speed as the stars near the center. This was a flagrant violation of known physics. It was like finding that Pluto orbits the Sun at the same speed as Mercury. These outlying stars were moving so fast that the gravity from the galaxy's visible matter couldn't possibly hold onto them. They should have been flung off into space eons ago. The galaxy should have torn itself apart. Rubin was a careful scientist. She studied dozens more galaxies. And everywhere she looked, she found the same impossible result: flat rotation curves. 60 different spiral galaxies all told the same story. The visible matter just wasn't enough. This was the moment Fritz Zwicky's ghost could no longer be ignored. What was saving these galaxies? The answer would forever change our understanding of home. The revelation. The invisible giant. The solution to the impossibly fast-spinning stars was as elegant as it was mind-bending. The visible galaxy, the beautiful spiral we call the Milky Way, is not the main event. It is merely a luminous decoration embedded in the center of a colossal, invisible sphere of dark matter. This is the galactic halo. So, how big is it? Recent data from incredible instruments like the European Space Agency's Gaia satellite has allowed us to map the halo's staggering extent. While the visible disk is about 100,000 light-years across, the true edge of our galaxy, the edge of its dark matter halo, is now estimated to be about 1,000,000 light-years from the center, giving it a diameter of nearly 2,000,000 light-years. Let that sink in. The visible part of our galaxy makes up only about 5% of its total diameter. If the dark matter halo were the size of a football stadium, the entire visible Milky Way, our home, with its hundreds of billions of stars, would be a single grain of sand on the 50-yard line. This isn't just about size, it's about mass. All the stars, gas, and dust we can see, the normal, or baryonic matter, makes up only about 15% of the total mass of the Milky Way. The other 85% is this invisible, mysterious dark matter. The shining galaxy we see is just the foam on the surface of a deep, dark ocean. Structurally, this halo has a couple of main parts. First, there's the asterisk stellar halo. This is a sparse, ghostly sphere of very old stars and ancient star clusters that extends for hundreds of thousands of light-years. It's like a graveyard of the galaxy's earliest history, containing less than 1% of the Milky Way's stars. Recent discoveries show this stellar halo isn't a perfect sphere, but is oblong and tilted like a football, likely the scar from a massive collision with a dwarf galaxy billions of years ago. But the real giant, the true scaffolding of our galaxy, is the asterisk dark matter halo. And even it isn't a simple sphere. The latest models from 2026 suggest it's a squashed, triaxial shape, an oblate spheroid oriented perpendicular to the starry disk of our galaxy. It permeates everything, and its gravity dictates the fate of everything within it. Without this massive halo, the gas and dust in the early universe never would have coalesced to form the majestic spiral we see today. This revelation completely redefines our cosmic address. But get this, brand new research in 2026 suggests even that isn't the whole story. It now looks like our galaxy's halo is embedded within a vast, pancake-like sheet of dark matter stretching for tens of millions of light-years, with our entire local group of galaxies along for the ride. This challenges the whole idea of an isolated galactic bubble, hinting that our true cosmic home is stranger and far more connected than we ever imagined. The evidence. How we see the unseeable. Proving something exists when you can't see it is one of the biggest challenges in science. So how have we become so confident in the scale of the Milky Way's dark halo? The answer is to watch the one thing it does interact with: gravity. Dark matter may be invisible, but its gravitational pull is profound and, it turns out, detectable. The main tool for seeing the unseeable is asterisk gravitational lensing. Einstein's theory of general relativity tells us that massive objects curve spacetime. Imagine spacetime as a stretched rubber sheet. A massive object, like a galaxy's dark matter halo, creates a huge, shallow divot in that sheet. When light from a very distant galaxy travels toward Earth, its path gets bent as it passes through our halo. From our perspective, that background galaxy looks distorted or stretched. By measuring the precise distortion of thousands of distant galaxies, astronomers can work backward and essentially weigh the invisible halo causing the bending. But the evidence goes even further back in time, to the asterisk cosmic microwave background. CMB, asterisk. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. This ancient light has tiny temperature fluctuations, the seeds of all future galaxies. Here's the key: if the universe only had normal matter, there wouldn't have been enough time or gravity for those seeds to grow into the galaxies we see today. Radiation pressure would have smoothed them out. Dark matter provides the solution. Since it doesn't interact with light, it could start clumping together much earlier, forming deep, gravity wells. When normal matter was finally free, it fell into these pre-existing dark matter scaffolds, forming the first galaxies. The patterns we see in the CMB only make sense if dark matter was there from the beginning. Finally, we see the halo's influence on our own cosmic neighbors. The Milky Way is surrounded by dozens of smaller dwarf galaxies, like the Large and Small Magellanic Clouds. By tracking the orbits of these satellite galaxies, scientists can map the gravitational landscape they're moving through. They've even detected a wake of stars left behind by the Large Magellanic Cloud as it sails through our halo, much like a ship leaves a wake in water. All these lines of evidence the impossible speed of stars, the bending of light, the structure of the early universe, and the dance of our satellite galaxies point to the same, inescapable conclusion. We are living inside a ghost. The ongoing hunt. What is this stuff? We've mapped its size and weighed its mass. We call it dark matter. But the simple, humbling truth is, we have absolutely no idea what it is. Dark matter is not a solution, it's a placeholder. It's a name we give to our ignorance, one of the most profound mysteries in all of science. For decades, the leading candidates were hypothetical particles called WIMPs, weakly interacting massive particles. The theory was elegant: heavy particles, born in the Big Bang, that stream through us by the billions every second, completely unnoticed. This idea spurred a global hunt. Scientists built incredibly sensitive detectors deep underground, hoping to catch the rare ping of a WIMP bouncing off an atom. But after decades of searching, the result has been a deafening silence. So, physicists are looking elsewhere. A different candidate gaining traction is the axion. Unlike WIMPs, axions would be incredibly lightweight. They were first proposed to solve a completely different problem, but scientists realized they had the right properties to be dark matter. Experiments are now underway, using powerful magnetic fields to try and convert these ghostly axions into detectable particles of light. But what if the problem isn't a missing particle at all? What if our understanding of gravity is wrong? This alternative idea is known as *MOND*, or modified Newtonian dynamics. MOND suggests that on the vast scales of galaxies, gravity doesn't get weaker as quickly as we thought. If gravity were slightly stronger over large distances, it could explain the flat rotation curves without any dark matter at all. While MOND has had some success, it struggles to explain things like gravitational lensing and the CMB, where the dark matter model works perfectly.
The search continues, pushing the boundaries of technology and theory. We're living through a pivotal moment. The answer, when it comes, won't just fill a blank in our models. It will herald a revolution in physics, opening up a whole new, dark sector of the universe with its own particles and forces, completely hidden from us until now. Exploring these cosmic mysteries is what drives science forward. The fact that most of our own galaxy is made of something we don't understand isn't a failure, it's an invitation. If you find this journey to the edge of knowledge as thrilling as we do, and you want to be there for the next great discovery, make sure you subscribe to our channel. Your curiosity is the fuel for our exploration. Redefining home. We started with a simple image, the Milky Way, a familiar, shining city of stars. We end with something far grander and more mysterious. We've learned that the galaxy we see is just a small, luminous port town on the shore of a vast, dark continent. Our home is not a 100,000 light-year disk, but a 2 million light-year sphere of influence, dominated by a substance we don't yet comprehend. The invisible halo isn't just something that surrounds our galaxy. In the truest sense, it is our galaxy. It is the gravitational skeleton, the cosmic nursery, the great, silent guardian that holds our starry home together. Its presence forces us to embrace a cosmos that is far more vast, more subtle, and more deeply mysterious than it appears to our eyes. Looking up at the night sky will never be the same. When you see that faint, glowing band of the Milky Way, remember that what you're seeing is just the visible evidence of something infinitely larger. You are staring into the heart of an invisible giant. We are all passengers, living inside a ghost, on a journey through a universe where the most profound truths are those that hide in plain sight. The greatest discoveries are not of new, distant worlds, but of the true nature of the place we've always been. The search for the identity of dark matter is not just a quest to understand the universe, it is a quest to understand our home. And the journey has only just begun. Part 2: The Visible Galaxy. If the true Milky Way is far larger than the shining band we see, then it is worth slowing down for a moment and lingering inside that band of light itself. Before we follow the gravity of the invisible halo out into the great dark beyond, it helps to understand the smaller, brighter home we already know. Because even if the visible galaxy turns out to be only a fraction of the whole, it is still a magnificent thing. It is the part that gave us our first clues. The part that filled human myths, guided travelers at night, and made our ancestors wonder whether the sky was not empty at all, but crowded with distant fires. On a truly dark night, far from city lights, the Milky Way does not look like a collection of separate stars. It looks like a pale river, a soft band of silver dust spilled across the sky. For most of human history, that was all it was to us, a mysterious glow. Beautiful, familiar, and impossible to fully understand from the ground. It looked flat and gentle from Earth, almost like a brushstroke. But that calm stripe in the sky is only the edge on view of something far grander. We are not looking at a ribbon. We are looking from inside a galaxy, outward through one of its crowded lanes. That is one of the strangest parts of our cosmic situation. We are trying to understand the Milky Way while living inside it, the way a person standing deep in a forest might try to describe the shape of the whole forest without ever rising above the trees. We cannot simply fly out and take a family portrait. We have to infer the structure from light, distance, motion, dust, and patience. And over time, a picture emerged. Not all at once, but slowly. A bright central region. A wide, thin disk. Curving arms rich with stars and clouds. And around all of that, a fainter halo of ancient stars. The visible Milky Way, the part made of stars, glowing gas, and dark dust, is often described as a barred spiral galaxy. That means it is shaped something like a great spinning disk, with a long bar of stars across the center, and spiral arms winding outward from that inner region. But even that description can be a little too neat, a little too tidy, compared with the real thing. Galaxies are not drawn with a compass. Their arms are not painted lines. Their edges are not sharp. They are living structures, if we may borrow a gentle metaphor, shaped by gravity, motion, turbulence, and time. Imagine a city seen from very high above at night. There are bright downtown regions, quieter suburbs, winding roads, industrial zones, dark parks, and neighborhoods at different stages of life. The Milky Way is like that, except on a scale so vast that even light, the fastest thing we know, needs 100,000 years or more to cross the visible disk from side to side. And within that span are hundreds of billions of stars, along with cold gas, warm gas, dust clouds, stellar nurseries, dead stars, and worlds that no human eye will ever see directly. The disk is where much of the visible action happens. This is the broad, flattened region where the spiral pattern lives. If you could somehow look at the Milky Way from the side, the disk would appear surprisingly thin compared with its width, more like a cosmic vinyl record than a sphere. That thinness tells a story. Over immense stretches of time, matter settled into orderly orbits around the galactic center, flattening into a rotating plane. Within that plane, stars circle the center in a slow procession, each following its own long path. Our own sun is one of them, traveling quietly through this disk as though it were just another commuter in a city too large to comprehend. And within the disk, not all neighborhoods are alike. Some regions are calm and populated by older stars. Others are busy, blue, and young, alive with star formation. Where clouds of gas and dust become dense enough, gravity begins to gather them inward. They collapse, heat up, and eventually ignite. A new star is born. This is why some parts of the Milky Way seem brighter and bluer than others. They contain massive young stars, brilliant and short-lived, lighting up the surrounding gas before burning through their lives in cosmic haste. Those spiral arms, though, deserve a slower look. They are easy to imagine as fixed structures, like the solid arms of a pinwheel. But they are better understood as patterns, crowded regions, places where material bunches up as it circles the galaxy. You can think of them almost like traffic slowdowns on a great orbital highway. Stars and gas move in and out, but the pattern remains. And when gas enters one of these denser regions, it can be compressed. Compression leads to star formation. So the arms become places of renewal, bright with newborn stars and veiled with the clouds that made them. For centuries, even understanding that much was a challenge, because visible light alone does not tell the whole story. Dust veils the central galaxy so effectively that if we relied only on ordinary sight, much of the Milky Way would remain hidden behind its own curtains. So astronomers learned to listen in other ways. Infrared light can pass through dust more easily. Radio telescopes can trace cold hydrogen gas stretching through the disk. Different wavelengths reveal different layers of the same galactic body, almost as if the Milky Way changes character depending on how you look at it. In one form it is a glittering river of stars. In another it is a map of gas. In another it is a skeleton of structure otherwise concealed. That, too, is part of the visible galaxy's lesson. Seeing is not only about eyes. It is also about methods, patience, and learning how light hides as much as it reveals. There are smaller structures within the visible Milky Way that make it feel less like a smooth machine and more like a place with texture. There are open star clusters, loose families of stars born together from the same cloud, still traveling through the galaxy in each other's company. Some are young and bright, blue and temporary, destined to drift apart over time as gravity from the wider galaxy slowly loosens their bond. Then there are globular clusters, older and denser, spherical swarms of ancient stars that hover in the galactic outskirts like relic lanterns from an earlier age. They are not part of the thin spiral pattern in the same way as the disk. They belong to a deeper history, one that reaches back toward the youth of the Milky Way itself. And when we talk about the galaxy as visible, it is worth remembering that much of what makes it beautiful would be invisible to human eyes standing in space. Some gas clouds glow only under particular conditions, lit by the harsh ultraviolet light of newborn stars. Some regions shine more clearly in infrared. Some of the Milky Way's grandest features are not really objects, but processes unfolding over millions of years. A spiral arm is not just a shape. It is motion organized into pattern. A bright nebula is not just a cloud. It is a place where radiation, gravity, and chemistry are briefly holding one another in a delicate balance. The visible galaxy is less like a still photograph and more like weather, except the weather lasts longer than civilizations. All of this helps explain why the Milky Way feels so strangely intimate and so impossibly remote at the same time. It is our home galaxy. We belong to it completely. Every star you have ever seen with your own eyes belongs either to the Milky Way or lies beyond it. And yet even the familiar stars overhead are only the thinnest local sample of a structure so large that most of it will always remain conceptual, something we understand through maps, models, and inference rather than personal sight. We live inside it, depend on it, orbit within it, and still only know it in fragments. There is something very human about that. To belong to something larger than your senses can hold. To live inside a mystery and gradually learn its shape. This gives the Milky Way some of its most beautiful contrasts. There is light everywhere, but also shadow. The dark lanes threading through the glowing band are not empty gaps. They are thick curtains of dust, blocking the starlight behind them. Invisible light, dust conceals. It creates those dramatic rifts and scars that cut through the brightness of the galaxy. Yet hidden inside many of those dark clouds are future stars. So even the darkness in the Milky Way is not a kind of absence. It is often a kind of waiting. If you were able to drift through one of those great molecular clouds, it would not look like a dramatic storm from a science fiction film. It would feel almost like nothing at all. The material is far too thin for that. And yet, spread across enormous distances, it contains enough matter to build clusters of stars, planets, and perhaps even new living worlds. The galaxy is full of these quiet reservoirs, these patient regions where tomorrow is being assembled grain by grain. Then there is the bulge, the swollen, crowded heart of the visible galaxy. Toward the center of the Milky Way, stars become far more numerous. The space between them narrows. Older stars dominate. Their light is warmer, more golden, more ancient in character. The central bulge is not merely a brighter patch. It is a record of a deeper past, a more crowded history. And hidden within that central region, behind dust and distance, lies the compact source we call Sagittarius A star, the gravitational anchor around which the larger visible galaxy turns. Our own place in all of this is strangely modest. We are not in the center. We are not in one of the most dramatic star-forming regions. We live out in the disk, in a quieter stretch known as the Orion Spur, between larger spiral arms. That location may not sound glamorous, but it is probably fortunate. The galactic center is crowded and intense. Radiation is stronger there. Stellar encounters are more frequent. Our region is calmer, more suburban, if you like, a place where a solar system can circle in relative peace for billions of years. That peaceful setting matters. It is easy to forget that our entire solar system is moving. Earth circles the Sun, the Moon circles Earth, but the Sun itself is also orbiting the center of the Milky Way, carrying all the planets with it. At roughly 230 million years per orbit, one galactic year is so long that the last time the Sun was in this same place around the galaxy, dinosaurs still walked the Earth. That means all of recorded human history, from the first cities to this quiet moment now, has unfolded during only the tiniest fraction of one orbit around our galactic center. There is something calming about that. Not because it makes us feel important, but because it places us gently inside a larger rhythm. Human life can feel hurried. A year feels significant. A decade can feel enormous. Yet the galaxy moves on another scale entirely, with an almost geological patience. It turns, forms stars, loses stars, stirs its dust, and carries whole solar systems with it, all without urgency. The visible Milky Way also has a kind of layered age to it. Some stars in the disk are young, hot, and bright. Others are older than the Sun by billions of years. Some clusters have orbited the galaxy for immense spans of time, preserving memories of earlier eras. When astronomers study the colors, motions, and chemistry of stars, they are not just counting lights in the sky. They are reading family histories. A star's composition can hint at when it formed. Stars born early in the galaxy's history tend to contain fewer heavy elements. Later generations inherit richer material, seeded by earlier stars that lived, died, and scattered their contents back into space. In that sense, the visible galaxy is not just a structure. It is an archive. The stars around us do not all belong to one moment. They belong to many moments layered together. Some were born in the Milky Way's early youth. Some came from smaller galaxies that were pulled in and absorbed long ago. Some are only now emerging from cold clouds. The galaxy we see is the result of mergers, collisions, calm periods, and bursts of creation. It is not a static portrait. It is a long memory made visible. And still, for all its beauty, the visible Milky Way is incomplete in a very important way. It gives the impression of being the whole galaxy because it is what our eyes notice first. Light has a way of convincing us that what shines is what matters most. But that is often not true in astronomy. The visible parts of the Milky Way are like the lit windows of a vast city seen from a distance at night. Beautiful, informative, and deeply meaningful, yes. But they do not show the roads beneath, the power grid, the underground foundations, or the invisible gravity holding the entire structure together. Even so, we should not rush past the visible galaxy just because it is not the whole story. It is the doorway through which the deeper mystery entered. We learned to measure our galactic home by watching stars move through this disk. We learned where dust hides the center. We learned how gas gathers into nurseries and how ancient clusters linger in the outskirts. The visible Milky Way is not a mistake. It is a clue. It is the luminous handwriting of a much larger system. If you could take a long, slow journey from the inner bulge outward through the disk, you would pass through regions of changing density, changing age, changing color. Near the center, the galaxy would feel crowded and bright. Further out, the neighborhoods would open. You would move through lanes of gas, through associations of young stars, through darker reaches where dust swallows light, through places where supernova remnants whisper that a star once ended there violently long ago. And farther still, the disk would thin. The visible population would become more sparse. The city lights would begin to fade. And that fading matters. Because it raises a natural question. Where does the Milky Way actually end? Does it end where the bright stars become scarce? Where the spiral structure fades? Where the gas becomes too thin to notice? Or does it continue in a form our eyes cannot follow? For a long time, the visible edge of the disk felt like a reasonable answer. There is a strong psychological pull toward what can be seen. We like boundaries that glow. We trust outlines. But the universe is under no obligation to shape itself around the limits of human sight. The stars in the visible disk are only one expression of the galaxy, not its full extent. Beyond the brighter, flatter regions of the Milky Way lie older stars in the halo, loose globular clusters, streams of torn dwarf galaxies, and then, beyond even those faint tracers, the far larger mass that does not shine at all. This is what makes the visible Milky Way so beautiful and so deceptive at the same time. It feels complete. It feels like the object itself. But in reality, it is more like the glowing core of something much larger. The part we can see is telling the truth, but not the whole truth. It is like hearing the music from one room in a vast house and assuming the house ends at the walls around you. And yet, perhaps that is not a failure of perception. Perhaps it is simply how discovery works. We begin with the bright things. We notice the stars. We map the dust lanes. We measure the disk. We find our place within the spiral pattern. Only then do we begin to sense that the visible galaxy, for all its splendor, behaves as though it is embedded in something larger, something heavier, something hidden. So before we leave the visible Milky Way behind, it is worth taking one last quiet look at it, at the thin starry disk turning in the dark, at the spiral arms where stars are born, at the dust clouds where light disappears, at the calm region where our sun makes its slow orbit, at the central bulge glowing through distance and obscurity. This is the home our eyes taught us to love, the home our ancestors imagined before they knew what a galaxy was, the home that is real, but not complete. And maybe that is why the Milky Way feels so hauntingly beautiful. Because even the part we can see is already almost too large for the mind to hold. A city of stars 100,000 light-years across. A rotating structure older than the sun. A layered history of births and deaths written in light and dust. To understand that this shining system is only the beginning, Only the visible surface of a larger, darker architecture does not make it less beautiful. It makes it more so. If these quiet journeys through the universe help you settle into rest, you can leave a like, subscribe, or simply share where in the world you are listening from tonight. It is always comforting to imagine these thoughts moving softly across many sleeping places at once. And as we keep moving outward, away from the bright lanes and into the harder questions, the visible Milky Way leaves us with one final lesson. Light is not the same as truth. Light is only what first reaches us. The deeper structure of the galaxy, the thing that truly defines its scale, may be hidden in darkness. To find that, we have to stop asking only where the stars are, and begin asking why they move the way they do. Because the next clue is not written in what the Milky Way looks like. It is written in how the galaxy behaves. Part 3, the first sign something was missing. The strange thing was not that the Milky Way looked mysterious. The strange thing was that it behaved badly. Not violently. Not dramatically. Not in some obvious way that shouted for attention. The stars still shone. The spiral arms still curved through the dark. The galaxy still looked, from a distance, like a graceful cosmic structure moving exactly as a galaxy should. But hidden inside that elegance was a quiet problem. The outer parts of galaxies were moving too fast. Far too fast. And once astronomers realized it, the old picture of the Milky Way could no longer hold. If you have ever watched a stone tied to a string and spun in a circle, you already understand the heart of the problem. The faster it moves, the more strongly the string must pull inward to keep it from flying away. In space, gravity plays the role of that string. A star moving around the center of a galaxy can remain in orbit only if gravity is strong enough to hold it there. If the inward pull is too weak, the star should drift outward, or at least move differently than it does. That sounds simple enough. And for a long time, astronomers assumed the Milky Way would follow the same basic logic as our solar system. In the solar system, the pattern is familiar. The planets nearest the Sun move fastest. Mercury races around in just 88 days. Earth takes a year. Neptune, far out in the cold, takes 165 years to complete one orbit. The farther you go from the Sun, the weaker the Sun's pull becomes, and the slower orbital motion should be. It feels intuitive because it is. Most of the solar system's mass is concentrated in the Sun, and so the rules are clear. Distance increases, gravitational grip weakens, orbital speed drops. Now imagine applying that same reasoning to the Milky Way. Much of the visible matter in a galaxy appears to be concentrated toward the middle. The central bulge is bright and crowded. The inner disk is denser than the outskirts. So astronomers expected that stars far from the galactic center would orbit more slowly than stars closer in. Not stop, of course. Just slow down in a way that made sense. The visible galaxy seemed to invite that expectation. And if that had been true, this story would be much shorter. But the universe, as it often does, declined to cooperate. Long before the Milky Way's own mystery came fully into focus, one of the earliest clues appeared not in our galaxy at all, but in a distant swarm of galaxies known as the Coma Cluster. In the 1930s, an astronomer named Fritz Zwicky studied how fast those galaxies were moving within the cluster. Zwicky was brilliant, sharp-tongued, and not especially known for gentle diplomacy. But whatever else may be said about him, he noticed something important. The galaxies in that cluster were moving so quickly that the cluster should not have remained together if only the visible matter were providing the gravity. It was as though the visible galaxies were only the tip of the mass, not the whole thing. Zwicky proposed that there must be additional unseen matter providing the missing gravitational pull. He called it dark matter. At the time, the idea was too strange, the data too early, and perhaps the man himself too abrasive for the astronomical world to fully embrace it. So the thought lingered at the edges of science for decades, like an unopened letter sitting quietly on a desk. Then, years later, the same basic problem appeared again. Only this time, it appeared inside individual galaxies themselves. And that made it much harder to ignore. In the 1960s and 1970s, astronomers began measuring the rotation of spiral galaxies more carefully. One of the most important figures in this work was Vera Rubin, an astronomer whose calm, meticulous approach would help reveal one of the deepest mysteries in modern science. Rubin, working with collaborators including Kent Ford, studied how stars and gas moved around the centers of galaxies. These measurements were not just decorative details. They were tests of whether gravity and visible matter told the same story. The result was deeply unsettling. Instead of slowing down as they moved farther from the bright central regions, stars in the outer parts of spiral galaxies often kept moving at nearly the same speed as stars much closer in. The expected drop in speed simply did not happen. The rotation curve, which should have risen and then fallen, instead flattened out. This may sound like a technical detail, but it was a genuine shock. A flat rotation curve meant the outer galaxy was orbiting as if much more mass existed than anyone could see. If visible stars, gas, and dust were all that was there, then the outer regions should not be moving the way they were. They should have been more loosely held, more leisurely in motion. Instead, they were racing along as though embraced by a much stronger gravitational field than the visible galaxy could account for. To make this feel less abstract, imagine walking around the edge of a huge spinning carousel. If the only support were in the center, you would expect the outer parts to behave differently from the inner parts. Now imagine finding that the outer edge is moving as if hidden machinery extends far beyond the visible structure, gripping it all the same. That was the feeling astronomers began to face. The visible galaxy was not enough. Something unseen had to be helping hold it together. And the Milky Way, our own galaxy, was not exempt. Studying the Milky Way is in some ways harder than studying other galaxies, because we are trapped inside it. We do not get the luxury of standing back and viewing the full disk from outside. But over time, astronomers found ways to measure how gas clouds, stars, and satellite objects moved through the galaxy. Piece by piece, the same pattern emerged. The outer Milky Way was behaving as though much more mass existed than the shining disk alone could provide. This is where the visible galaxy began to lose its innocence. Not its beauty, but its completeness. The stars were still where they were. The spiral arms still shone. The band of the Milky Way still stretched softly across dark skies. But now the galaxy seemed to be whispering that it was heavier than it looked. If you are listening late at night, perhaps half asleep already, there is something almost eerie about that idea. A structure made mostly of what cannot be seen. A galaxy whose visible light is not the whole body, but only its glowing center. The Milky Way, in this new picture, was beginning to resemble a lantern hung inside a much larger invisible house. What made the case stronger was repetition. Astronomers did not see this problem in one galaxy only, or two. They saw it again and again. Spiral galaxies across the universe showed the same broad behavior. The outer stars were moving too fast for the visible matter alone. That repetition matters in science. One odd result can be a mistake. 100 similar results become a pattern. And a pattern, when it survives careful testing, becomes something much more serious. It is easy now, looking back, to imagine that everyone immediately understood the importance of this. But science rarely moves like a single flash of lightning. It is usually slower than that. People question the measurements. They test instruments. They try alternative explanations. They ask whether the stars are being counted correctly, whether the gas has been underestimated, whether some hidden ordinary matter might solve the puzzle. Good science is skeptical, and it should be. But as the evidence improved, the problem remained. Something was missing. That word missing is important. Because at first, the problem did not feel like a complete theory. It felt like an absence. A gap between what could be seen and what gravity demanded. And gravity, unlike appearances, is difficult to charm. It does not care how elegant the galaxy looks. It responds to mass, whether that mass is bright, dim, dusty, cold, or invisible. If stars in the outer galaxy move quickly and remain bound, then enough mass must be there to keep them bound. The galaxy cannot negotiate its way around that. It cannot pose beautifully and hope the equations go easier on it. Motion reveals truth. In astronomy, what things do often tells us more than how they look. This was one of the great turning points in how we understand galaxies. For centuries, stars had dominated our emotional picture of the cosmos. They are what we see. They are what we name. They are what fills stories, myths, poems, and childhood wonder. But here was a humbling possibility. Perhaps stars were not the main substance of a galaxy after all. Perhaps they were only the illuminated parts, the decorative lights on something much larger and stranger. The Milky Way, then, could no longer be described honestly as only a city of stars. It was becoming something else in the scientific imagination. A visible disk nested inside a broader gravitational structure. A bright inhabitant of an unseen mass. There is also a beautiful irony here. Human beings first came to understand the galaxy by looking at its light. But the deeper reality began to emerge from motion. Not from brightness, but from behavior. The stars themselves became witnesses. Their speeds, their orbits, their refusal to slow down properly, all testified that the visible galaxy was incomplete. And once that possibility entered the conversation, astronomers had to ask harder questions. If there is extra mass, where is it? Is it made of ordinary matter that simply does not shine? Could it be cold gas, dead stars, brown dwarfs, black holes, or objects too faint to detect easily? Or was the missing mass something more exotic, a new kind of matter altogether? At first, many hoped the answer might still be ordinary. Science does not invent invisible substances casually if familiar explanations remain possible. There were serious attempts to see whether all the missing gravity could be explained by unseen but otherwise normal objects. Perhaps the galaxy was full of dim bodies that emitted little light. Perhaps enormous clouds of faint gas had been overlooked. Perhaps our census of the galaxy was incomplete in a mundane way. But the scale of the problem kept growing. The missing mass was not just a small correction. It was huge. In galaxy after galaxy, the invisible component seemed to outweigh the visible one by a large factor. The more carefully astronomers measured, the more obvious it became that the bright matter we know so well was not doing most of the gravitational work. That realization is one of the quiet revolutions of modern science. It did not come with one dramatic explosion or one single discovery date that changed everything overnight. It arrived through careful observation, repeated measurements, and a growing discomfort with the old picture. The visible universe, at least on galactic scales, appeared to be only a minority contribution to the total mass. For the Milky Way, this changed the meaning of home. Earlier, the galaxy had seemed like a grand but mostly understandable structure, one built from stars, gas, dust, and the central mass hidden in the bulge. Now that picture was being stretched outward by an invisible hand. The galaxy was no longer just what glowed. It was whatever held the glowing parts together. And that is a profound shift in perspective. Imagine discovering that the walls of your house are not the true boundaries of the home you live in. Imagine learning that the visible rooms are only the lit center of a much larger, unseen structure surrounding you. That is something like what happened to astronomy in the age of dark matter. The Milky Way did not merely become larger. It became stranger. Still, it is worth moving slowly here, because the idea can become too abstract if we rush. The missing mass problem was not a mystical hunch. It came from a simple mismatch between expectation and observation. Based on visible matter, outer stars should slow down. But they did not. Therefore, either our understanding of gravity was incomplete, or there was more mass present than met the eye. Those two options have shaped much of the discussion ever since. One path says gravity works differently on galactic scales than we once thought. The other says gravity is behaving normally, but most of the mass is hidden. Both ideas have inspired serious work. But for many astronomers, dark matter became the leading explanation because it seemed to account not just for galaxy rotation, but for a whole family of cosmic clues. Even before we get to those larger clues, the basic emotional force of the Milky Way mystery is powerful enough on its own. It tells us that our eyes, useful as they are, do not automatically reveal the most important part of a thing. A galaxy can appear delicate and luminous while being dominated by something unseen. Light, once again, turns out not to be the full story. Perhaps that is one reason this subject settles so naturally into the quiet hours. It invites a softer kind of wonder. Not the wonder of fireworks or spectacle, but the wonder of realizing that what seems complete may only be surface. That our galaxy, so familiar in imagination, may actually be structured by something invisible passing silently through and around it. And the Milky Way is not merely surrounded by that hidden presence. It is shaped by it. Its stars orbit within it. Its gas settles inside its gravity. The very stability of the visible disk may depend on a much larger mass we cannot see directly. The bright galaxy is, in a sense, suspended inside a deeper darkness. If these calm journeys into cosmic mysteries help you rest, feel free to leave a like, subscribe, or share where you're listening from tonight. It is always lovely to imagine these quiet thoughts traveling softly from one part of the world to another. By this stage in the story, astronomers were no longer asking whether something odd was happening. They were asking what the hidden structure might look like. If invisible matter explains the fast-moving stars, then it cannot be packed only into the bright center. It must extend well beyond the visible disk, forming a much larger envelope of mass. Not a thin luminous spiral, but a broad, dark halo. And that idea changed everything. Because once you begin to think of the Milky Way not just as a disk of stars but as the glowing center of a vast invisible halo, the question of scale opens again. The galaxy's true boundary is no longer where the starlight fades. It is wherever that invisible gravitational reach still holds. So the first signs something was missing were not really signs of emptiness. They were signs of hidden fullness. The galaxy was not lacking mass. It was overflowing with mass we could not see. The stars in the outer Milky Way were not behaving badly at all. They were simply obeying a larger structure than we had yet learned to imagine. And that is where the story begins to turn. Because once astronomers accepted that the visible galaxy was only part of the Milky Way, the next challenge was to map the unseen part. Not with eyes, but with motion, gravity, and the faint traces left behind by objects moving through an invisible sea. The visible Milky Way had introduced us to our home. The strange motions of its stars were about to reveal its true size. Part 4: What dark matter might be. By the time astronomers accepted that something unseen was shaping the Milky Way, a new kind of question began to rise out of the silence. Not where is it? Not even how much of it is there. But what is it, exactly? That question sounds simple when spoken aloud. Almost childlike, in the best possible way. What is it? It is the kind of question we ask when we first encounter something strange. A shell on a beach. A light in the sky. A sound in another room. We want to name it, place it, understand what kind of thing we are dealing with. And yet, with dark matter, that simple question becomes one of the deepest in modern science. Because we can describe what dark matter seems to do much more easily than we can describe what dark matter actually is. That distinction matters. For now, dark matter is a name for an effect before it is a fully understood substance. It is the label we give to the missing gravity, the invisible mass, the hidden part of the galaxy that appears to be there even though it does not shine, glow, or reflect light in any obvious way. We know something is pulling. We know something is holding stars in place. But knowing that something is there is not the same as knowing its nature. And there is something almost hauntingly beautiful about that. For thousands of years, human beings looked at the sky and wondered whether the universe was stranger than it appeared. Dark matter is one of the clearest answers we have ever received. Yes, it is stranger, much stranger. Because most of the matter shaping our galaxy may not be made of the familiar stuff of stars, planets, dust, oceans, stone, blood, bone, or breath. The ordinary matter that makes up the world of daily life may be only a small part of the cosmic inventory. Before going further, it helps to slow down and clarify one thing. Dark matter does not mean dark in the everyday sense. It is not black smoke drifting through space. It is not shadow. It is not the absence of light, like an empty room after sunset. In astronomy, dark here means something closer to invisible. It does not interact with light in the normal ways that ordinary matter does. It does not glow when hot, reflect when illuminated, or block light the way a dust cloud can. It seems to pass through the universe without announcing itself to our eyes. That alone is strange enough. But it becomes even stranger when you realize how much of the universe may be involved. The stars, planets, gas clouds, and galaxies we see are thought to make up only a minority of the matter in the cosmos. The rest, if the dark matter model is right, is hidden. Not far away in some separate realm, but threaded through and around the same universe we already inhabit. It is all here. We are simply not built to see it directly. Naturally, scientists did not begin by assuming some entirely new form of matter had to exist. Science is usually more cautious than that. The first instinct was to ask whether the missing mass could simply be made of ordinary things we had not yet counted properly. Perhaps the galaxy contained huge numbers of faint, cold objects, burned-out stars, brown dwarfs, rogue planets, small black holes, clouds of gas too dim to notice. In other words, maybe the universe had not changed. Maybe our census was just incomplete. This was a reasonable hope. After all, the universe has often surprised us by hiding ordinary things in difficult places. Dust can block starlight. Gas can spread thinly across huge regions. Dim objects can easily escape detection. It made sense to ask whether the missing mass problem would go away if we simply looked harder and counted better. But over time, that explanation began to fray. There did not seem to be nearly enough faint ordinary matter to account for the gravitational effects being measured. And ordinary matter, even when dim, usually leaves some trace. It absorbs light, emits radiation under certain conditions, or interacts with other familiar matter in ways we can eventually notice. The hidden mass seemed too quiet for that. Too abundant, too smooth, too unwilling to reveal itself in ordinary ways. So the possibility of a more exotic answer began to take shape. What if dark matter is made of particles? That idea has guided much of the modern search. We already know that ordinary matter is built from particles. Electrons, protons, neutrons, and the deeper structures beneath them form the material world we know. So one natural thought was that dark matter might also be particulate, a sea of previously unknown particles moving through space, carrying mass but barely interacting with normal matter at all. This is where the story becomes delicate, because it is easy to let the language become too technical. But at heart, the idea is quite simple. Imagine a kind of matter that has weight, that responds to gravity, and that helps shape galaxies, but that almost never bumps into ordinary matter in a way we can easily detect. It would pass through us, through the Earth, through stars, through the galaxy itself, mostly unnoticed. Not because it is magical, but because the kinds of interactions we rely on to detect things, especially interactions involving light, would be extremely weak or absent. One of the most famous categories proposed for dark matter was a class of hypothetical particles called WIMPs, short for weakly interacting massive particles. The name is clumsy, but the idea behind it is elegant. These particles, if they exist, would be much heavier than the particles of light and would interact with ordinary matter only through gravity and perhaps the weak nuclear force. In plain terms, they would be difficult to catch. They would not form glowing clouds. They would not make shiny planets. They would not build atoms in the familiar way. But they could fill the large-scale structures of the universe and provide the missing mass galaxies seem to need. For a long time, WIMPs became one of the leading candidates. Scientists built deep underground experiments, hidden beneath mountains or layers of rock, hoping to isolate their instruments from cosmic noise and catch the faintest sign of a passing dark matter particle. The idea was almost poetic. Somewhere in the dark silence below the Earth, detectors waited for a whisper from the unseen universe. But so far, the silence has mostly remained silence. That does not mean the idea is dead. Science is rarely that simple. It may be that dark matter is more elusive than expected, or that the particles interact even more weakly than we imagined. But the longer the silence continues, the more open the field becomes to other possibilities. Another candidate, quieter in reputation but deeply fascinating, is the axion. If WIMPs are imagined as relatively heavy hidden particles, axions would be astonishingly light. So light, in fact, that they would behave in ways that feel more like a subtle cosmic field than a familiar clump of matter. They would be everywhere, gentle and ghost-like, almost impossible to notice directly. And yet, in enormous numbers, they could still contribute significant mass across cosmic scales. It is one of the charming oddities of physics that sometimes a particle first appears in theory for one reason, and then later becomes useful in solving a completely different mystery. Axions were not originally invented to explain galaxies, but they turned out to have properties that made them interesting dark matter candidates. Experiments now try to detect them in creative ways, often by using strong magnetic fields and exquisitely sensitive instruments that can listen for the faintest conversion of these hypothetical particles into a trace of light. Again, nothing definitive has yet emerged. But that, too, is part of the atmosphere of this mystery. Dark matter is not a solved puzzle being retold around a campfire. It is an open frontier. The search is still alive. The identity of the hidden mass remains uncertain. There are other candidates as well. Some physicists have imagined sterile neutrinos, relatives of known particles but even more aloof. Others have considered primordial black holes, ancient black holes formed very early in cosmic history. These would not be dark matter particles at all, but dark compact objects scattered across the cosmos. The idea is intriguing, but current evidence suggests they are unlikely to account for all of dark matter by themselves. Still, the possibility reminds us how wide the imagination of science must sometimes become when the universe refuses to fit into older categories. And then there is the more radical possibility. What if dark matter is not matter at all? That question does not arise from fantasy. It arises from humility. Whenever the universe presents us with a mismatch between observation and theory, we must consider two broad options. Either there is more stuff than we thought, or the rules governing the stuff are incomplete. In the case of galaxies, that means one alternative to dark matter is the idea that gravity itself behaves differently on large scales than our usual models predict. This family of ideas is often grouped under modified gravity theories, and one of the most discussed forms has been called MOND, or modified Newtonian dynamics. The basic thought is that perhaps gravity becomes stronger than expected when accelerations are extremely small, as they are in the outer reaches of galaxies. If that were true, stars could move faster without requiring huge amounts of invisible mass. There is a certain elegance to this possibility. After all, science has revised its laws before. Newton's gravity gave way, in a deeper sense, to Einstein's general relativity. So it would be unwise to assume our current understanding is already final. Some aspects of galactic behavior can, in fact, be described surprisingly well by modified gravity ideas. And yet the broader cosmic picture seems to favor dark matter more strongly. When astronomers look not just at rotation curves, but at clusters of galaxies, gravitational lensing, the growth of large-scale structure, and the afterglow of the early universe, the dark matter framework tends to explain more of the evidence in one coherent picture. It is not perfect. No major scientific mystery is. But it has proven remarkably powerful. Still, I think there is something healthy in remembering that the question remains open in spirit, even when one explanation leads in practice. The universe does not owe us certainty on demand. Sometimes it allows only layered confidence. Enough evidence to move forward, but not enough to stop wondering. If dark matter is real as a substance, and not merely a correction to gravity, then it raises a curious question about the world around us. Could dark matter be here, right now? The answer, most likely, is yes. If the Milky Way is embedded in a great dark matter structure, then our solar system, our planet, your room, your resting body listening now, all exist inside it. Dark matter would not be floating out only in the far, remote halo like some distant cosmic fog. It would extend through the galaxy, including the region around the Sun, though probably very thinly by ordinary standards. Enormous numbers of hypothetical particles might pass through your hand every second without leaving a sensation. The silence of that image is almost impossible to picture. An invisible rain, falling through the earth, through walls, through oceans, through us, almost without contact. And yet that is exactly the kind of universe dark matter suggests. One where the most abundant matter may be all around us, and still untouched by human senses. This is also why dark matter would not gather itself into familiar objects the way normal matter does. Ordinary matter interacts electromagnetically. It can lose energy, cool down, collapse into clouds, form stars, planets, and people. Dark matter, as far as we can tell, does not do that, or at least not easily. It does not seem to clump into glowing disks or rocky worlds. Instead, it spreads into large, diffuse structures, broad gravitational frameworks within which ordinary matter can settle. In a way, dark matter seems less like architecture we live on and more like the hidden landscape gravity moves across. That may be one reason the idea of a dark matter halo becomes so important. If dark matter does not collapse into bright, compact structures the way normal matter does, then the Milky Way's hidden mass would naturally take on a very different shape from the thin luminous disk. The stars and gas form a flat rotating system because they can collide, radiate energy, and settle. Dark matter, by contrast, seems to remain puffed out, extended, and diffuse. It surrounds rather than imitates the visible galaxy. But before we fully step into the halo itself, it helps to stay a little longer with the emotional meaning of the question. What is dark matter? At the moment, the truest answer may be this: we do not yet know. Not in the satisfying, complete sense. We have candidates. We have elegant theories. We have beautiful experiments buried underground, suspended in mines, sealed in laboratories, hidden from ordinary noise, all waiting for one small sign. We have cosmological models that describe how this invisible component shapes the universe on giant scales. But the thing itself remains elusive. That should not be mistaken for failure. It is one of the most natural and human stages of knowledge. First, something behaves strangely. Then we discover a hidden cause. Then we begin the slow work of naming that cause more precisely. Dark matter is not embarrassing because we do not yet fully understand it. It is magnificent for exactly that reason. It tells us the universe still has unopened rooms. And for a sleep channel like this, perhaps that is one of the softest forms of wonder. Not the wonder of sudden spectacle, but the wonder of hidden depth. The idea that the Milky Way, familiar from childhood, is suspended in a substance no one has ever held in their hand. The idea that most of the mass shaping our galaxy may be made of something beyond ordinary experience. The idea that the stars, beautiful as they are, might only be the visible punctuation marks in a sentence mostly written in darkness. If these calm explorations of the universe help you settle into rest, you can leave a like, subscribe, or gently share where you are listening from tonight. It is always comforting to imagine these quiet thoughts passing through different cities, different time zones, and different sleepers under the same sky. There is also a subtler philosophical shift dark matter asks of us. For much of history, visible things felt like the default reality. What shines is what matters. What can be touched is what counts. What can be seen is what is there. Dark matter complicates that instinct. It reminds us that reality can be structurally dominated by things that do not present themselves directly. The visible galaxy is not false, but it may be secondary. It is the part of the Milky Way our senses can meet, not necessarily the part that carries most of the mass. That thought can feel unsettling at first, but it can also be strangely calming. There is humility in it. The universe is not arranged for our convenience. It does not guarantee that the deepest truth will also be the brightest or easiest to notice. And perhaps that is why astronomy remains so beautiful. It keeps teaching us that light is only one way of knowing. So when we ask what dark matter might be, we are really standing at the threshold of two mysteries at once. One is physical. What is the hidden substance? If substance it is, that outweighs the stars. The other is conceptual. How do we build a picture of reality when most of the important structure cannot be seen directly? Those questions now travel together. And in the Milky Way, they lead us naturally to shape. Because whatever dark matter is, it does not seem to arrange itself the way normal matter does. It does not flatten into a bright disk. It does not trace the spiral arms. It does not announce itself with stellar nurseries or glowing nebulae. Instead, it appears to form a much larger, more diffuse envelope around the visible galaxy. A vast region of gravitational presence surrounding the shining Milky Way like an unseen atmosphere. That is the next step in the story. First, astronomers realized something was missing. Then they began to suspect that the missing presence was not just extra mass, but a new kind of matter, or at least evidence of a deeper law still hidden from us. And next, they had to imagine its shape. Not a river of stars. Not a flat luminous pinwheel. But something larger, rounder, darker, and far more immense than the visible Milky Way had ever suggested. The question was no longer only what dark matter might be. It was also this: if our galaxy lives inside it, then what does our invisible home actually look like? Part 5: The idea of a galactic halo. If dark matter does not shine, does not settle into stars, and does not gather itself into the familiar shapes of ordinary matter, then the next question becomes almost visual. What form would it take? This is where the story of the Milky Way begins to change shape in the mind. Up to this point, it is easy to picture the galaxy as a glowing spiral, a thin disk with arms turning slowly through space. That image is so deeply rooted in modern astronomy, and in popular imagination, that it almost feels complete. When people hear the words Milky Way, they tend to picture a shining pinwheel of stars. Beautiful, structured, almost elegant enough to feel finished. But once dark matter enters the story, that picture can no longer stand alone. Because the visible galaxy, for all its beauty, is too flat, too small, and too light to explain the gravity astronomers were measuring. Something broader had to be there. Something extending well beyond the starry disk. Something that did not follow the spiral arms, did not light up in the same way, and did not collapse into the neat visible structure we instinctively imagine. The answer that emerged was not a second disk, and not a hidden copy of the visible galaxy. It was something far more diffuse. A halo. The word halo is a gentle one. It sounds almost delicate, almost decorative. It may bring to mind a ring of light around the moon, or a soft circle painted above the head of a saint in old religious art. But in astronomy, a halo is not a little ornament. It is often the larger structure. the quiet, extended domain around the brighter heart of a galaxy. And in the case of the Milky Way, the halo may be the truest expression of the galaxy's full size. To understand why, it helps to think for a moment about how different kinds of matter behave. Ordinary matter, the kind that makes stars, gas clouds, planets, and people, interacts in many ways. It collides. It heats up. It cools down. It radiates energy. It can lose momentum and settle into thinner, denser shapes. That is one reason galaxies made of ordinary matter often develop disks. Gas clouds bump into one another, gradually flattening into a common plane as they orbit. Stars born from that gas inherit some of that structure. Over long timescales, a broad, spinning disk emerges. Dark matter seems to behave very differently. It does not appear to collide much, if at all, in the ordinary sense. It does not shed energy through light the way hot gas does. It does not cool and sink into a thin luminous layer. So instead of forming a flat disk, it is thought to remain in a more extended, puffed-out structure, surrounding the visible galaxy on all sides. Not a sheet of light, but a three-dimensional gravitational envelope. That is the basic idea of a galactic halo. A much larger region around the visible galaxy, containing matter that is spread out rather than concentrated into a bright spinning plane. And once that idea takes hold, the Milky Way begins to feel different. Not smaller than before, but deeper. The glowing disk becomes something like the bright center of a much larger body. The part we can easily see becomes, in a sense, only the lit core of a larger invisible home. There is a helpful way to imagine this, though like all analogies it has limits. Think of a city at night seen from an airplane. The roads, buildings, and neighborhoods shine below in sharp patterns of light. That glowing city is real, and if you knew nothing else, you might think the lights mark the whole meaningful extent of the place. But perhaps beneath and around that lit city lies a much larger geography, dark hills, river basins, soil, older foundations, invisible infrastructure, power lines, and the larger land on which everything rests. The visible lights are not false. They simply do not tell the whole story. In the same way, the Milky Way's disk of stars is real and stunning, but it may sit inside a much larger gravitational terrain that does not shine. The idea of a halo also helps solve a geometric problem. If stars in the outer parts of the galaxy are moving too fast to be held by the visible matter alone, then the extra mass cannot be packed only into the bright center. It must extend outward, far beyond the region where most of the stars live. It has to remain present in the outskirts, still contributing gravitational pull. A vast halo naturally provides that. The farther out you go, the more of that invisible mass you enclose within your orbit, helping explain why rotation curves stay high instead of dropping away sharply. In time, astronomers realized that the Milky Way's halo is not just one thing in a simple sense. It contains layers, or perhaps it is better to say it contains different populations. One is the stellar halo, made of actual stars, though far fewer and more widely spread out than the stars of the disk. The other, much larger and much more important in terms of mass, is the dark matter halo. Together they form a broader region around the visible galaxy, but they are not identical. The stellar halo is like a faint ghost of the galaxy's deeper past. It contains very old stars, many of them poor in heavy elements, which suggests they formed early in cosmic history. It also includes globular clusters, dense spherical swarms of ancient stars orbiting well above and below the galactic plane. Some of these stars may have belonged to the Milky Way from very early on. Others may have been stolen, in a cosmic sense, from smaller galaxies that were pulled apart and absorbed over billions of years. This is one of the most quietly beautiful aspects of the halo. It is not just a region of space. It is a record of galactic memory. The Milky Way did not grow in perfect isolation. It appears to have fed on smaller companions, swallowing dwarf galaxies over immense spans of time. Their stars were stretched out, dispersed, and folded into the halo. Even now, astronomers can detect streams of stars arcing around the galaxy, the torn remains of smaller systems gradually being woven into the Milky Way's larger body. In a sense, the stellar halo is filled with fossils. It is the galaxy's old battlefield, old archive, old graveyard, and old inheritance all at once. And yet, as fascinating as the stellar halo is, it is still only the faint visible trace of something much larger. The true giant is the dark matter halo. This dark halo is not made of starlight. It does not sparkle in telescopes. It does not announce itself in photographs. Its presence must be inferred through motion, gravity, and the behavior of everything moving within it. And according to the modern picture, it extends far, far beyond the visible disk. The Milky Way's familiar spiral structure, perhaps around 100,000 light-years across, may sit inside a dark matter halo whose diameter stretches into the range of nearly 2 million light-years or so, depending on how one defines its outer edge. That comparison is so extreme that it can lose meaning if spoken too quickly. So it helps to slow it down. Imagine the visible Milky Way as a softly glowing island. Even that island is vast enough to contain hundreds of billions of stars. It is already a scale that defeats ordinary thought. Now imagine that the island is sitting in the center of an invisible ocean vastly larger than the island itself. The visible galaxy is not the whole land. It is the lit central territory of a much broader domain. That is what the halo does to our sense of scale. It quietly informs us that the galaxy does not end where the lights fade. This also means that if someone asks, "How big is the Milky Way?" the answer depends on what you mean by Milky Way. Do you mean the bright disk of stars? Do you mean the visible structure? Do you mean the outermost gas? Do you mean the ancient stellar halo? Or do you mean the entire gravitational domain defined by dark matter? Each answer describes something real, but only the last one begins to approach the full scale of the galaxy as modern astronomy understands it. And there is another subtle point here. When people hear the word halo, they often imagine something neat and spherical, like a perfect shell around the galaxy. But nature is usually less tidy than our first diagrams. The Milky Way's halo is not likely to be a perfect sphere. It may be stretched, squashed, tilted, lopsided in places, and shaped by the galaxy's long history of mergers, interactions, and motion through the local group. Even the stellar halo shows evidence of asymmetry and ancient disruption. The dark halo, too, may be more like a softly distorted ellipsoid than a flawless ball. That makes sense, really. A galaxy is not built in a laboratory. It forms over billions of years through accretion, collapse, collision, and gravitational improvisation. The halo is the outcome of that history, not a geometric ideal. Still, the general picture remains powerful. The visible disk lies in the middle, thin and bright. Around it extends a much larger realm, sparse in stars but rich in gravitational importance. And beyond the visible galaxy's comfortable boundaries, the halo continues. Quietly, invisibly, holding. This shift in perspective changes not just the size of the Milky Way, but its identity. Earlier, the galaxy seemed defined by stars, by structure we could see, by spiral arms, glowing gas, and the central bulge. Now it begins to seem that these things are more like the decorated inner rooms of a larger unseen house. The halo is not an accessory. It is not a fringe detail added on later. It may be the main framework within which the galaxy exists at all. Without a dark matter halo, galaxies like the Milky Way might never have formed in the way we know them. In the early universe, ordinary matter alone would have had a harder time gathering itself efficiently into large structures. But dark matter, not interacting with light, could begin clumping earlier. It provided gravitational wells, hidden scaffolding into which gas later fell. In that sense, the halo is not just a container around the galaxy. It is part of the reason the visible galaxy exists in the first place. That is a remarkable reversal of instinct. We naturally assume the visible parts are primary. But the Milky Way may owe its spiral beauty to a structure no eye can see. The invisible halo may be less like a shadow cast by the galaxy and more like the deep architecture from which the galaxy emerged. If you sit with that thought for a moment, it becomes almost meditative. Our home galaxy, so full of light, may be fundamentally organized by darkness. The grand starry river seen from Earth is not floating alone in empty space. It is moving within an enormous unseen presence. The stars are not simply scattered in a void. They are orbiting inside a hidden landscape of mass. And because we live inside the galaxy, we live inside that halo too. The Earth does not orbit out at the edge of the dark matter halo. We are much closer to the center than that. We live in the disk, yes, but the halo surrounds and permeates the larger galactic environment. It is part of our cosmic address whether we notice it or not. We sleep, wake, age, and build civilizations inside a gravitational structure we cannot directly see. There is something soft and humbling in that thought. It does not threaten daily life. It does not change the weight of your room or the feel of the night air. But it does change perspective. It suggests that what feels local is nested inside something vast and invisible. That the Milky Way itself is not merely a bright place in space, but a luminous feature within a much deeper and quieter mass. The halo also blurs the notion of where a galaxy ends and where intergalactic space begins. If the visible disk fades into sparse outer stars, and those outer stars exist inside an even larger dark matter envelope, then the edge of the galaxy becomes more like a gradual transition than a sharp boundary. The Milky Way does not stop the way a table ends at its edge. It thins. It softens. It extends into lower and lower densities until its gravitational reach gives way to the larger dynamics of the local group. That is one reason the exact size of the halo can be difficult to define cleanly. Different astronomers may use different practical definitions, based on mass density, gravitational influence, orbital behavior, or simulation models. But the broad truth remains. The halo is immense, and it extends far beyond the bright spiral arms. This matters especially when thinking about neighboring galaxies. The Milky Way is not alone. It shares its region of space with Andromeda, the Triangulum galaxy, and many smaller companions. Each major galaxy is thought to possess its own dark matter halo. And these halos are so large that the space between galaxies is not always as empty as it sounds. In some cases, halos may approach, overlap, or interact gravitationally long before the visible disks come anywhere near one another. That gives the universe a different texture than the old picture of isolated islands in a blank sea. Galaxies are not only bright objects separated by emptiness. They are extended gravitational territories, embedded in a larger cosmic web. The halo is part of what makes that true. Still, for all its scale, the halo remains elusive in a very human way. No one looks through a backyard telescope and sees the Milky Way's dark halo shining back. No amateur skywatcher points upward and says, "There it is." The halo belongs to the realm of inference, to careful mapping of motion, to the patient mathematics of gravity, to the faint tracers of stars, clusters, and satellites whose behavior reveals the shape of the unseen. That may be why the idea feels so powerful once it settles in. It asks us to trust a reality deeper than appearance. To accept that the brightest part of something may not be the largest, the heaviest, or the most defining part. The halo is not obvious. But once the evidence points to it, the visible Milky Way can never feel quite complete again without it. If these quiet journeys help you drift into rest, you can leave a like, subscribe, or simply share where you're listening from tonight. It is always lovely to picture listeners under different skies, all resting inside the same invisible galactic home. There is also something emotionally satisfying about the word halo itself once you understand what it means here. It gives the Milky Way a kind of layered dignity. A bright disk of stars at the center, yes, but also a larger, dimmer, older, more mysterious region surrounding it. The halo is where the galaxy's ancient fragments drift, where old stars wander, where globular clusters trace long patient orbits. And beyond even those visible hints lies the great dark halo, the hidden mass that makes the whole structure heavier and larger than it appears. In a sense, the halo is the Milky Way learning to exceed the limits of sight. We began with a galaxy that looked like a river of stars. Then we found that the stars were moving as though guided by an unseen hand. Then we considered what dark matter might be. And now the emerging picture is this. Our galaxy is not just a bright spiral floating in emptiness. It is the luminous center of a vast, extended halo, a much larger gravitational home whose true boundaries are written in darkness. And once that idea is accepted, a new challenge follows naturally. If the halo is real, how do we map it? How do you measure something you cannot photograph directly? How do you weigh a structure made mostly of invisibility? How do you trace the outline of a ghost that only reveals itself by the way it pulls on everything else? That is the next step in the story. Because imagining the halo is one thing, measuring it is another. And it is in that measurement, patient and indirect, that astronomers began to discover just how enormous our invisible home might really be. Part 6: Measuring the Invisible. There is a peculiar challenge at the heart of astronomy. The largest parts of things are often the hardest to see. A planet can be photographed. A moon can be tracked. A bright star can be studied in exquisite detail. Even a distant galaxy, glowing softly across millions of light years, can be captured as a visible shape against the dark. But the Milky Way's dark matter halo does not offer that kind of cooperation. It does not shine for our telescopes. It does not outline itself politely against the sky. It does not arrive with labels, edges, or a visible surface. And yet, astronomers have still found ways to measure it. That is one of the quiet miracles of science. When nature refuses to reveal something directly, we learn to study the traces it leaves behind. We look for what it bends, what it pulls, what it speeds up, what it holds together, and what it changes. In the case of the Milky Way's halo, almost everything we know comes from that kind of indirect listening. We do not see the halo itself. We see what living inside the halo does to everything else. And in some ways, that makes the story even more beautiful. Because this is not really a story about one telescope taking one perfect picture. It is a story about patience, about motion measured over years, about starlight compared across vast distances, about tiny shifts in position that become, slowly, a map of gravity. The dark matter halo is not photographed into existence. It is reconstructed, piece by piece, from the way the galaxy behaves. The first and most obvious clue comes from motion. If you want to know how much mass is hidden inside a system, one of the best things to do is watch how objects move within it. This is true on small scales and large ones. In the solar system, the motion of the planets tells you the sun is massive. In a galaxy, the motion of stars and gas tells you how gravity is distributed across the whole structure. That is how the missing mass problem first came into focus, and it is still one of the main ways astronomers probe the halo. Imagine standing in a great dark house at night, with no lights except a few floating lanterns. You cannot see the walls. You cannot see the beams. You cannot see the shape of the whole structure. But if the lanterns are swinging on invisible strings, and if you can measure how fast they move and where they turn, then gradually you can infer the architecture around them. That is very close to what astronomers do with stars in the Milky Way. Some stars orbit within the bright disk, as we have already seen. But others range far above and below the plane of the galaxy, out into the halo itself. These more distant stars are especially valuable, because their motion is influenced by the broader gravitational field of the Milky Way, not just the dense visible disk. By measuring how fast they move, and in what direction, astronomers can estimate how much mass must be present to guide them. This is where modern surveys have changed everything. For much of history, astronomy was limited by a simple problem. The sky is vast, and precise motion is hard to measure. From Earth, stars appear fixed to the naked eye, like pinpricks on a dome. But of course they are not fixed. They move, slowly from our perspective, but constantly. Over time, with enough precision, their drift across the sky can be recorded. And when that drift is combined with measurements of distance and speed toward or away from us, astronomers can reconstruct a star's path through space. One of the great gifts to modern astronomy has been the European Space Agency's Gaia mission. Gaia has measured the positions, distances, and motions of enormous numbers of stars with astonishing precision. It is, in a sense, helping us turn the Milky Way from a static image into a living map of motion. And once you have motion on that scale, the invisible parts of the galaxy begin to reveal themselves more clearly. Gaia does not detect dark matter directly. It does something more subtle. It shows us how stars move through the galaxy's gravitational field. That field, in turn, reflects the total mass present, both visible and invisible. By studying stellar motions in different regions, especially far from the bright central disk, astronomers can build models of how massive the halo must be and how far it extends. But stars inside the Milky Way are only part of the story. Another powerful tool comes from the galaxy's companions. The Milky Way is not alone. It is orbited by a population of smaller dwarf galaxies, modest companions moving through its gravitational domain. Some are faint and difficult to detect. Others, like the Large and Small Magellanic Clouds, are prominent enough to be seen from southern skies as misty patches of light. These satellite galaxies are precious to astronomers because they behave like test particles in the Milky Way's larger field. Their orbits, speeds, and histories contain information about the mass surrounding them. If the Milky Way were only the visible disk, those satellites would move one way. If the galaxy is embedded in a vast dark matter halo, they would move another. The difference matters. Take the Large Magellanic Cloud, for example. It is not just a beautiful neighboring galaxy. It is also a heavy object moving through the Milky Way's outer gravitational environment. As it travels, it appears to disturb stars in the halo and tug on the structure around it. In some studies, astronomers describe this as a kind of wake, a subtle gravitational stirring left behind as the cloud moves through the halo. That is a remarkable idea if you pause to feel it. An invisible ocean announcing itself not by what it looks like, but by the ripples left by something moving through it. The outer halo also contains globular clusters, those ancient spherical swarms of stars we mentioned earlier. These clusters orbit far from the galactic center, and because they are bright enough to trace at large distances, they become useful markers. Their paths are shaped by the Milky Way's total mass. By measuring their motion, astronomers gain another set of clues about the halo's gravitational reach. Then there are stellar streams, one of the most poetic tools in the whole story. A stellar stream is formed when a smaller object, often a dwarf galaxy or globular cluster, is gradually torn apart by the Milky Way's gravity. Its stars do not vanish. They stretch out into long, thin ribbons, looping across the sky like torn silk. These streams preserve memory in motion. They trace the path their original system once followed, and because of that, they respond exquisitely to the shape of the surrounding gravitational field. In a way, a stellar stream is like a strand of smoke drifting through a room. You may not see the air itself, but the smoke reveals its currents. In much the same way, stellar streams reveal the hidden structure of the halo. If the dark matter halo were perfectly smooth and perfectly spherical, streams would evolve one way. If the halo is lopsided, clumpy, stretched, or shaped by past interactions, the streams behave differently. Astronomers can compare the observed form of these streams with computer models and infer which kind of halo best explains them. One of the beautiful things about this method is that it feels less like brute force and more like listening. The galaxy tears apart smaller companions, yes, but in the long stretched trails they leave behind, it also writes down its own gravitational signature. And yet measuring the halo is not only about mapping individual objects. Sometimes it is about asking a broader question. How fast must something move to escape the Milky Way entirely? This is known as the escape velocity. If you launch an object upward from Earth, it needs a certain speed to escape Earth's gravity. The same logic applies to the galaxy as a whole. A star moving through the Milky Way must reach a certain speed to break free from the galaxy's gravitational grip and never return. The higher that escape speed is, the more mass the Milky Way must contain. So astronomers look for very fast stars, especially those in the Sun's neighborhood or farther out, and study how close their speeds are to the galactic escape velocity. If many stars are still bound despite moving extremely fast, that implies the galaxy is heavier than the visible matter alone would suggest. Once again, motion becomes a weighing scale for the invisible. There is something almost elegant about this. The galaxy has no visible weighing station, no cosmic scale hanging in the dark, but gravity itself acts as the measurement. Fast stars ask the question. The halo answers. Of course, none of these methods work in isolation. That is part of what makes the final picture convincing. If only one line of evidence pointed toward a large halo, scientists would remain cautious. But many lines converge. Rotation curves, halo stars, satellite galaxies, globular clusters, stellar streams, escape speeds. Each method has uncertainties, yes. Each depends on assumptions, models, and limited observations. But together they form a kind of chorus. And the chorus keeps singing the same song. The Milky Way is much more massive, and much more extended, than the visible galaxy alone. Computer simulations also play an important role here. Astronomers do not simply observe and then guess. They build virtual galaxies inside powerful simulations, varying the amount of dark matter, the shape of the halo, the merger history, and the motions of stars and satellites. Then they compare these simulated galaxies to the real one. Which models reproduce the Milky Way we actually observe? Which ones create realistic stellar streams? Which ones match the motions of dwarf galaxies? Which ones produce the right sort of outer halo? This is not because simulations replace reality. It is because they allow astronomers to test how different invisible structures would affect visible behavior. If a certain halo model produces motions that match the actual Milky Way, that model becomes more plausible. If it fails, it can be discarded. In that sense, simulations are like laboratories for invisible architecture. And still, even with all this sophistication, there is a certain softness to the work. The halo's edge is not a painted line. The Milky Way does not come with a crisp outer shell that can be measured with a ruler. The farther out you go, the less dense the structure becomes. The transition from galaxy to surrounding space is gradual. So when astronomers talk about the size or mass of the halo, they are often speaking in terms of definitions and thresholds. Where does the density drop below some chosen level? How far out does the galaxy's influence remain dominant? What radius best captures the region in which the Milky Way is gravitationally bound as a coherent system? This is why you may hear slightly different numbers in different discussions. That does not mean scientists are confused about whether the halo exists. It means nature has fuzzy boundaries, and measurement depends partly on what exactly you are trying to define. A shoreline is real even if the tide makes its precise line move. The halo is much the same. It is real, but not sharply cut. There is another method, more dramatic in concept, that has helped support the existence of dark matter on larger cosmic scales, though it is less direct for our own Milky Way. This is gravitational lensing. According to Einstein's theory of general relativity, mass bends space-time, and light follows those bends. So a large mass can act a bit like a lens, distorting the image of objects behind it. In clusters of galaxies, this effect can be measured quite strikingly. The visible matter alone is not enough to create the observed distortions, which strongly suggests the presence of additional unseen mass. For the Milky Way's own halo, lensing is not the primary tool in the same simple way, because we are inside the system rather than viewing it from the outside as a neat foreground lens. But the broader success of gravitational lensing studies across the universe strengthens the general case that dark matter is not just a local accounting trick inside galaxies. It seems to be part of a larger cosmic pattern. The same is true of the cosmic microwave background, the faint afterglow from the early universe. That ancient light contains subtle patterns which, when analyzed carefully, point toward a cosmos in which ordinary matter alone is not enough to explain how structure formed. Dark matter fits into that bigger picture. So while the Milky Way halo is measured through local motions and local tracers, those measurements sit inside a much larger web of evidence. The galaxy's invisible mass is not an isolated oddity. It appears to be one expression of a deeper cosmic rule. Still, I think the local methods carry a special beauty, because they are so intimate. We are not merely studying abstract equations in a remote universe. We are measuring the invisible structure of our own home. The stars above us, the satellite galaxies circling us, the ancient streams stretched across our sky, all are helping us understand the larger body in which we live. And the more carefully astronomers have measured, the more complex the halo has begun to look. It is probably not perfectly smooth. It may contain substructure, smaller concentrations of dark matter left over from the galaxy's growth and mergers. It may be slightly flattened or elongated rather than spherical. It may be influenced by the Milky Way's interaction with Andromeda and with the broader local group. In some studies, the stellar halo appears tilted or asymmetrical, perhaps as the scar of long-ago collisions. The dark halo itself may also be shaped by that history. This reminds us that the Milky Way is not a machine assembled once and left alone. It is a historical object, a living gravitational structure shaped by time. Measuring the halo, then, is not just a matter of finding one number. It is a matter of recovering a biography. How heavy is the galaxy? How far does its invisible influence extend? What companions has it absorbed? What distortions remain from those encounters? What hidden wake is still being raised by the Magellanic Clouds moving through its outskirts? Even uncertainty becomes part of the story here, not as a flaw, but as a sign of how alive the science still is. New data continues to refine the picture. Gaia has transformed the field, but it has not ended the questions. More distant halo stars are being mapped. More faint dwarf galaxies are being discovered. Better models are being built. And each refinement changes our sense of the Milky Way a little. The broad truth remains stable, while the details grow richer. If these calm explorations of the universe help you settle into sleep, you can leave a like, subscribe, or gently share where you are listening from tonight. It is always comforting to imagine this story drifting softly through many quiet rooms beneath the same galaxy. Perhaps the most remarkable part of all this is what it says about human knowledge. No one has touched dark matter. No one has scooped a sample of the Milky Way's halo into a container. No one has taken a photograph and circled the outer boundary with a pen. And yet by watching motion, by comparing maps, by tracing ancient stellar debris, and by following gravity's fingerprints, we have begun to measure something vast and unseen. We are, in a sense, cartographers of invisibility. That phrase may sound poetic, but it is also accurate. The old age of exploration mapped coastlines and continents. Modern astronomy maps invisible mass. Both kinds of work rely on clues, patience, and courage in the face of incomplete knowledge. Both begin with uncertainty and end with a gradually sharpened picture of where we really are. And that brings us naturally to the next question. Once you have measured the halo, once you have watched stars race through it, once you have tracked satellite galaxies and ancient streams and built models of the invisible structure around us, what do the numbers actually say? How large is the Milky Way's halo, really? How far does our galaxy extend once you stop measuring only by starlight and start measuring by gravity? Because the answer is stranger than our ordinary image of the Milky Way ever prepared us for. The glowing spiral most people imagine as the galaxy may turn out to be only a small illuminated center. The true Milky Way, measured by the reach of its hidden mass, is something much larger, something deeper, something wide enough to make our visible home feel almost like the bright core of a ghostly empire. Part 7. How large the halo may be. There is a moment in almost every cosmic story when the numbers stop feeling like numbers. At first, they arrive politely. A few thousand, a few million, a star here, a cloud there. Your mind still tries to cooperate. It still tries to picture what is being described. But then astronomy keeps going. The scales widen. The distances stretch. The language remains calm, while the imagination begins to slip. And eventually, there comes a point where the number is no longer something you can truly visualize. It becomes something you can only stand beside, quietly, and try to respect. The size of the Milky Way's dark matter halo is one of those numbers. Because once astronomers began measuring the galaxy not only by its visible stars, but by the full reach of its gravity, the Milky Way stopped looking like a 100,000 light-year spiral city and started looking more like a vast invisible kingdom with a bright little capital at the center. That shift is so large that it deserves to be approached slowly. Most people, when they imagine the Milky Way, are imagining the visible disk, the spiral arms, the central bulge, the broad shining structure where most of the stars live. That picture is not wrong. It is simply incomplete. The visible galaxy really is enormous. A disk roughly 100,000 light-years across is already beyond the scale of ordinary human comprehension. Light itself, traveling faster than anything else in nature, would still need 100,000 years to cross that bright disk from one side to the other. And yet, measured against the dark matter halo, that visible galaxy begins to feel strangely small. Current estimates vary depending on how astronomers define the halo's outer edge, but the broader picture points towards something astonishing. The Milky Way's halo may extend to around 1,000,000 light-years from the galactic center, perhaps a little less in some models, perhaps a little more in others. That means the full diameter of the halo could approach something like 2,000,000 light-years across. Pause there for a moment. Not because the sentence is complicated. It is not. But because its meaning deserves room. The visible Milky Way, the glowing disk most people think of when they hear the word galaxy, may be only a small inner region of a much larger structure whose true gravitational body stretches outward for nearly 2,000,000 light-years. That is not a minor correction. That is not like learning a city has one extra neighborhood you forgot to include. That is like learning the city is actually the lit center of a country. And perhaps the most disorienting part is how ordinary the sky still looks from Earth. If the Milky Way's true scale is so immense, why does the galaxy not seem that way to us? Because the larger part does not shine. The night sky gives us the visible Milky Way, the river of stars, the dusty central glow, the band of light across the darkness. It gives us only the luminous fraction, the part made of ordinary matter that produces or reflects radiation in ways we can detect more easily. The dark halo does not announce itself in the same language. So the Milky Way appears much smaller than it really is, in the same way a great mountain range might look modest if you could see only the snow on its highest ridges and not the full stone body beneath. The halo changes the scale of home in a way that is both humbling and strangely intimate. Because when we say the Milky Way may stretch across nearly 2 million light-years, we are not talking about some other galaxy, or some distant abstraction far beyond concern. We are talking about the structure we already live inside. The Earth, the Sun, the planets, the Orion Spur, the visible disk, all of it belongs to a galactic body much larger than the old bright picture suggested. And yet, even these huge numbers come with a kind of softness. Astronomers do not point to a crisp shell and say, "There, that is the exact boundary." The halo is not a solid wall. It is not a sharp sphere. Its density gradually decreases with distance. Its outer reach depends partly on how one defines the edge. Are we speaking about the region where matter is still strongly bound? The region where the average density exceeds a certain threshold? The region where the Milky Way's gravitational influence remains dominant over nearby structures? Different definitions yield slightly different answers. That can sound frustrating at first, as though science is being vague. But really it is just being honest. Nature often has blurred boundaries. A shoreline moves with the tide. An atmosphere fades into space rather than ending like a brick wall. A forest becomes grassland gradually, tree by tree. The Milky Way's halo is similar. It is real, but its edge is a transition rather than a line drawn in ink. Even so, the broad scale remains astonishing. Whether one uses a more conservative estimate or a more expansive one, the halo is vastly larger than the visible disk. That is the essential truth. The galaxy's real gravitational body extends far beyond the starlight. It can help to use comparison, even if all comparisons eventually fail. Imagine shrinking the visible Milky Way until it is the size of a dinner plate. In that same scale, the dark matter halo would be more like a broad dome or sphere extending far beyond the plate, enclosing a much larger volume around it. Or imagine the visible galaxy as a glowing little island in the center of an invisible sea whose shoreline lies far beyond what the island itself suggests. Or imagine a lantern hanging in the middle of a vast, dark hall. The lantern is bright and real, but it is not the hall. It merely reveals that the hall exists. That is what the halo does to our understanding of the Milky Way. It forces us to stop identifying the galaxy only with what glows. And once that perspective settles in, all sorts of other things begin to change as well. For one thing, the Milky Way becomes less isolated than it first appears. If its dark halo reaches outward for such an enormous distance, then the space between galaxies is not always simple emptiness. Our neighboring great spiral, Andromeda, also has its own halo. The distance between the Milky Way and Andromeda is only a few million light-years. That sounds comfortably large until you remember that each galaxy may possess a halo extending roughly a million light-years or so. Suddenly the two systems do not feel like tiny lights in a blank void. They feel more like vast gravitational domains approaching one another across a narrower gulf than we once imagined. In a very real sense, the Milky Way's halo brings us closer to our neighbors. Not visually. The sky does not look more crowded, but structurally, gravitationally, cosmically. Andromeda is not simply another spiral sitting alone in darkness. It is another massive system with its own invisible envelope, its own deep gravitational body. The future encounter between the Milky Way and Andromeda, expected billions of years from now, is therefore not merely a meeting of two bright disks of stars. It is the slow interaction of two enormous halos long before the visible galaxies truly merge. Their outer realms, their invisible dominions, may begin influencing each other well in advance of any dramatic collision of starlight. That thought alone changes the emotional texture of intergalactic space. It becomes less empty, less silent in a simple sense, and more like a vast field of overlapping influences. But let us come back to our own halo, because its internal scale remains almost too large to absorb. A million light-years from the center means that the halo extends outward enormously beyond the Sun's position in the galaxy. We are about 26,000 light-years from the galactic center, which already feels like a grand cosmic address. But compared with the full dark matter halo, that means we live quite deep inside the Milky Way's inner regions. We are not somewhere near the edge of the galaxy's true body. We are far from it. In terms of the visible disk, yes, we are somewhere out in the galactic suburbs. But in terms of the halo, we are still close to the bright inner heart. That is one of the gentler shocks of the whole subject. It reminds us that our sense of being on the outskirts depends entirely on which galaxy we mean, the visible one or the full one. And perhaps that is why the dark matter halo feels so philosophically rich. It reveals that scale is never only about size. It is also about definition. What counts as the Milky Way? What part of the galaxy do we mean when we say home? The answer has expanded. Home is not merely the starry disk. It is the much larger gravitational structure embracing the disk. Astronomers sometimes describe the visible matter as only a minority of the Milky Way's total mass. Most of the galaxy's mass appears to reside in dark matter. So the halo is not just larger than the bright part. It is also, in a real sense, more massive, more structurally dominant, and more defining. The visible Milky Way may be the part we know emotionally, the part we paint, photograph, and admire. But the halo may be the part that tells the galaxy how to behave. It determines how strongly stars are held in the outer regions. It shapes the motion of satellite galaxies. It governs much of the Milky Way's large-scale gravitational reach. In a deep and quiet way, it may be fair to say that the halo is not merely around the galaxy. It is the larger reality of the galaxy, of which the visible part is only one luminous expression. And that can be difficult to hold in the mind because we are so trained by everyday life to equate visibility with importance. The visible part of a tree is the tree, we think. The visible part of a building is the building. The visible part of a wave is the wave. But on cosmic scales, that instinct begins to fail. The Milky Way's shining disk may be more like the foam at the top of a much deeper body. There is also the question of how the halo compares with the structures around it. At some point, the Milky Way's own halo is no longer the only influence that matters. We live inside the local group, a small collection of galaxies gravitationally associated with one another, including Andromeda, the Triangulum Galaxy, and many dwarf galaxies. The Milky Way's halo is one major component of that neighborhood, but not the whole neighborhood itself. So as the halo extends outward, it gradually enters a larger context. Its outer edge becomes part of a broader gravitational conversation involving nearby galaxies and the shared history of the local group. This, again, softens the notion of boundaries. The universe is not built from separate sealed boxes. It is built from structures nested inside larger structures, disks inside halos, halos inside groups, groups inside filaments, filaments inside the great cosmic web. The Milky Way's dark matter halo is enormous on human terms, yet it is also only one part of a still larger cosmic architecture. That is not meant to make the halo feel less impressive. Quite the opposite. It helps place it properly. The halo is vast enough to redefine our idea of the galaxy, yet even it is connected to larger systems. The universe does not really deal in isolated objects. It deals in relationships, in gradients, in mutual influences spread across astonishing distances. And there is another layer to this story. The exact shape and extent of the halo may have changed over time. Galaxies are not fixed statues. They grow, absorb smaller companions, respond to nearby masses, and slowly evolve over billions of years. The Milky Way's halo, too, is part of that long history. It formed early, probably growing through the accumulation of dark matter and the merging of smaller structures. Over time it likely developed substructure, distortions, and scars from interactions with dwarf galaxies and with the larger environment. So when we speak of the Milky Way's halo today, we are speaking not only about an object, but about the latest state of an ancient process. This matters because size is not only a measurement, it is also a story of formation. A halo a million light-years across did not simply appear finished one day like an inflated balloon. It emerged through the gradual assembly of the Milky Way itself, through a long cosmic history of gathering and shaping matter. The visible disk settled inside a pre-existing dark matter scaffold. Smaller galaxies were pulled in and torn apart. Streams of stars were left behind. Satellite systems traced long paths through the outskirts. And all the while, the dark halo continued defining the broader gravitational territory around the growing galaxy. So when astronomers estimate the size of the halo, they are not merely describing a static sphere in space. They are describing the present reach of a historical structure that has been evolving for most of cosmic time. That thought gives the Milky Way a kind of quiet majesty. Our home galaxy is not just a collection of stars. It is an old, layered, invisible empire of gravity with a luminous city in the center. It has memory. It has absorbed other systems. It has extended its reach through billions of years. And we live in one small bright neighborhood within it. If these calm journeys through the universe help you settle into sleep, you can leave a like, subscribe, or gently share where you are listening from tonight. It is always comforting to imagine listeners spread across different countries and time zones, all quietly resting inside the same galactic halo. There is also something deeply calming about the scale itself, once the first shock wears off. A halo nearly 2 million light-years across is so far beyond everyday life that it can loosen the grip of smaller worries. Not by dismissing them, but by placing them in a gentler frame. The Milky Way has been carrying its stars through darkness for billions of years. The Sun has orbited within its inner regions through ages longer than human language. The halo has held satellite galaxies, ancient streams, and invisible mass in patient relation across distances that light itself crosses only over immense spans of time. Compared with that, our own hurried clocks begin to soften. And maybe that is part of the value of astronomy in the quiet hours. It does not solve the ordinary troubles of life directly, but it restores scale. It reminds us that the universe is patient, that great structures can remain coherent without haste, that reality is larger, older, and calmer than the frantic surface of a single day. Still, the halo's size is not important only because it is emotionally soothing or philosophically rich. It is scientifically powerful as well. Its enormous extent helps explain why outer stars remain bound, why satellite galaxies orbit as they do, and why the Milky Way participates in the larger dynamics of the local group the way it does. Size here is not just drama. It is function. The galaxy behaves differently because its true gravitational body is so large. And once that is understood, a new question arises almost immediately. If the halo is this immense, then the Milky Way cannot be special in having one. Other galaxies must also possess halos of their own. The same invisible architecture may surround spiral galaxies throughout the universe, which means our galaxy is not merely an isolated curiosity. It may be one local example of a universal pattern. That realization opens the story outward again, because the Milky Way's halo, however immense, may itself be one strand in a larger dark framework connecting galaxies across cosmic space. The invisible home around us may be part of a much greater invisible design, and that is where the story turns next. From the huge scale of our own halo, to the possibility that halos are not isolated at all, but part of a still larger web in which galaxies live, move, and slowly gather. Part 8. The Milky Way inside a larger web. Once you accept that the Milky Way is far larger than its starlight, another quiet thought begins to form. Maybe our galaxy is not floating alone at all. For a long time, it was easy to imagine galaxies as islands. Bright, self-contained structures scattered through a dark and mostly empty sea. Each one a separate kingdom of stars, with long silent distances between them. That picture was never completely wrong. Galaxies really are separated by enormous gaps. The universe is still, in many places, astonishingly sparse. But the deeper astronomy has looked, the less those gaps have felt like perfect emptiness. And the more we understand dark matter, the more galaxies begin to look less like isolated islands and more like luminous knots in a much larger, largely invisible network. This is one of the most beautiful shifts in modern cosmology. The Milky Way does not merely sit in space. It belongs to a structure. Not just the visible structure of its own spiral disk. Not even only the hidden structure of its own dark matter halo. It belongs to a wider environment, a cosmic neighborhood, and beyond that, to a still larger web that stretches across the universe. So to understand the full meaning of the Milky Way's dark matter halo, we have to zoom out again. Not all at once. Slowly. Gently. The way the universe seems to prefer. Let us begin close to home. The Milky Way is part of what astronomers call the local group. This is the small collection of galaxies gravitationally associated with our own. It includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies orbiting or drifting between the larger ones. On a human scale, this already sounds vast. And it is. The distances involved are measured in millions of light years. But in the language of the universe, the local group is still just a local neighborhood, a modest gathering inside something much larger. The important thing is this. The Milky Way's halo does not stop existing just because other galaxies are nearby. Andromeda has its own halo. Triangulum has its own. The dwarf galaxies may have smaller halos of their own as well. So the space inside the local group is not simply black emptiness with a few bright objects sprinkled into it. It is a region of overlapping gravitational territories, invisible domains of mass extending far beyond the visible stars of each galaxy. That changes the emotional feel of space. It becomes less like a blank ocean with a few tiny lanterns on it, and more like a landscape with valleys, hills, currents, and invisible boundaries. The galaxies are the bright landmarks. But the real structure, the hidden terrain that shapes how they move, lies mostly in darkness. This is part of what makes dark matter so powerful as an idea. It changes not only what galaxies are made of, but how galaxies relate to each other. It reveals that the universe is structured from the invisible outward. The visible galaxy is often the most beautiful part, but not always the most structurally important part. And once that lesson is learned locally, it begins to scale upward. Because the Milky Way's halo is not just a strange feature of our own galaxy. It appears to be part of a larger pattern. Galaxies across the universe behave in ways that suggest they, too, are embedded in dark matter halos. Spiral galaxies, elliptical galaxies, galaxy groups, and massive clusters all seem to carry more gravitational influence than visible matter alone can explain. Again and again, the visible universe appears to be nested inside a larger hidden framework. That framework, on the largest scales, is often called the cosmic web. This phrase sounds dramatic, but it is actually rather gentle once you understand it. The cosmic web is not a spider's web in any ordinary sense. It is not made of strings you could touch. It is the large-scale arrangement of matter across the universe, shaped by gravity over billions of years. Galaxies are not distributed evenly in all directions like dust floating in still air. Instead, they tend to gather into filaments, clusters, and sheets, with enormous emptier regions, known as voids, between them. If you could see the universe on the largest scales, not just the stars, not just the galaxies, but the underlying distribution of matter across hundreds of millions of light years, it would look less like a random spray and more like a vast interconnected pattern. Great strands and intersections. Dense nodes where many galaxies cluster together. Long bridges of matter stretching between them. And huge, quieter gaps where relatively little matter resides. The Milky Way, then, is not merely inside a halo. It is inside a galaxy, inside a group, inside a web. And this web is thought to be shaped largely by dark matter. That is because dark matter seems to have played a crucial role in structure formation very early in the history of the universe. Ordinary matter interacts with light, which in the young universe made it slower to collapse into dense structures. Dark matter, by contrast, did not couple to light in the same way. It could begin gathering earlier, forming the invisible gravitational scaffolding on which ordinary matter later collected. In that picture, galaxies are not the first architects. They are more like the glowing inhabitants of a structure dark matter helped create in advance. This is one of the most humbling ideas in astronomy. The visible universe may have grown inside a pre-existing invisible skeleton. If you like, you can imagine the early universe as a place where the first great quiet structures formed in darkness. Dark matter gathered into faint gravitational patterns, clumps, and filaments long before stars lit up the cosmic night. Then, over time, ordinary matter fell into those gravitational wells, cooled, condensed, and formed galaxies. The stars came later. The light came later. The visible beauty of the cosmos may have been, in some sense, a secondary flowering on top of an earlier unseen order. That does not make the stars less beautiful. If anything, it makes them more beautiful. Because now they feel like something emerging from hidden depth. This larger picture also reframes the Milky Way's halo itself. The halo is not simply a bubble around our galaxy with nothing much to do beyond holding stars in place. It is also part of a wider environment, shaped by the history of matter gathering across the local group and the nearby web of cosmic structure. Our galaxy's halo likely formed by accreting smaller dark matter structures, pulling in dwarf galaxies, and gradually assembling itself within the larger flow of matter around it. So the halo is not just a boundary. It is a history. Every galaxy's halo carries memory of how that galaxy formed. The small dark matter clumps that merged into larger ones. The dwarf companions that were absorbed. The filaments that fed matter inward. The neighboring gravitational fields that gently influenced its growth. In that sense, the halo is less like a static shell and more like the current shape of a very old cosmic process. And when we zoom out even more, galaxy groups and clusters begin to reveal something similar on their own scale. A cluster of galaxies is not simply many galaxies sitting near one another by chance. It is usually held together by an enormous shared gravitational field, much of it again attributed to dark matter. The galaxies move within that deeper mass, much as stars move within the halo of a single galaxy. The same pattern repeats. Visible structures nested inside larger invisible structures. Light inside darkness. Motion revealing what sight alone cannot. This repetition is one of the most persuasive aspects of the dark matter picture. The same broad logic seems to work on many scales. Galaxies appear heavier than their visible matter suggests. Clusters appear heavier than their visible matter suggests. The growth of structure in the early universe also points toward hidden mass. The more scales astronomy examines, the more often it encounters the same quiet truth. There is more here than light can account for. And yet there is something deeply calming in the cosmic web once the first abstraction fades. At first, it can feel cold. Large-scale structure. Filaments. Halos. Nodes. These can sound like technical terms, almost too mathematical to feel emotionally real. But if you sit with them longer, another feeling emerges. The universe is connected. Not intimately in the sentimental sense, but structurally. Galaxies are not lone accidents floating meaninglessly apart. They are part of an immense architecture. The Milky Way is not an isolated ornament. It belongs to a wider order. There is comfort in that. Even if the scales are beyond comprehension, the principle is familiar. Things belong to larger things. Rooms belong to houses. Houses belong to streets. Streets belong to cities. Cities belong to continents. In the cosmos, stars belong to galaxies. Galaxies belong to halos. Halos belong to groups and filaments. And all of it belongs to a universe whose structure is richer than the eye alone suggests. This is also why the space between galaxies is more interesting than it first sounds. When people hear intergalactic space, they often imagine nothing at all. A total absence. A kind of cosmic blank. But even in the more open regions between visible galaxies, there can still be diffuse gas, gravitational influence, dark matter, and the faint traces of past interactions. The space between galaxies may be sparse, yes, but it is not always simple. It is shaped by fields, flows, and history. And in some regions, especially within groups or clusters, halos and matter distributions may influence one another in subtle overlapping ways. Think again of the Milky Way and Andromeda. Their bright disks are still far apart, but their halos stretch outward far beyond what the stars alone suggest. Long before the visible galaxies merge, their dark matter environments may already be participating in a larger shared future. The eventual collision between the Milky Way and Andromeda, billions of years from now, is not the sudden meeting of two isolated bright pinwheels. It is the culmination of a much longer gravitational relationship already unfolding through their larger invisible structures. That makes cosmic time feel very different. What looks separate in the short term may already be connected in the long term. What appears distant in starlight may be nearer in gravity. And perhaps that is the cosmic web's gentlest lesson. The visible spacing between things does not always describe their deeper relationship. There is also growing evidence, in recent years, that the Milky Way's halo may be influenced by structures even broader than the simple image of a neat isolated sphere. Some studies suggest the galaxy may sit within more extended distributions of matter linked to the local group environment. There are even ideas that our galaxy's halo, Andromeda's halo, and the surrounding dark matter environment may be better understood as part of a larger shared context, not just completely separate bubbles side by side. That does not mean the Milky Way ceases to be its own galaxy. It does mean that nature is often less cleanly divided than our diagrams. The universe loves gradients, overlap, and layered belonging. And when you think about it that way, the old image of galaxies as isolated star islands begins to soften into something more realistic and more beautiful. They are still islands in one sense, but islands with invisible coastlines extending far into surrounding waters, all of them shaped by deeper currents and older tectonics beneath the surface. This broader web also helps explain why dark matter remains such a central idea in cosmology. If the mystery existed only at the level of one unusual galaxy, scientists might still suspect some local mistake. But the pattern appears almost everywhere. The universe keeps behaving as though hidden matter is part of its structure. The web itself, the clustering of galaxies, the formation of large-scale patterns, all become easier to understand if dark matter is part of the cosmic inventory. Of course, that does not mean every detail is settled. Science is still working. Measurements improve. Models refine. Simulations become more sophisticated. Competing ideas continue to be tested. But the broad story has become increasingly compelling. The universe seems to have grown through an invisible architecture that ordinary matter later illuminated. In that sense, stars are not the bones of the universe. They are more like the lanterns hanging from the bones. That may be one of the softest and most profound reversals in all of astronomy. We begin life assuming light tells the whole story. Then we learn that the structure holding galaxies, groups, and clusters together may be mostly unseen. We look up and admire the Milky Way's bright band, only to discover that what we see is a local glow inside a much larger dark framework extending across the cosmos. And once that thought fully settles, our galaxy begins to feel less like an endpoint and more like an address. Not the whole house. Not the whole city. Just our place within something bigger. If these calm explorations of the universe help you rest, you can leave a like, subscribe, or gently share where you are listening from tonight. It is always comforting to imagine people in different corners of the earth listening under the same hidden web of stars and darkness. There is also a subtle emotional shift here that I think is worth pausing for. The cosmic web can sound cold at first, almost mechanical. But really, it restores a kind of belonging. Not personal belonging in the everyday sense, but cosmic belonging. The Milky Way is not just some lonely object drifting without context. It has neighbors. It has a larger environment. It participates in flows of matter and gravity extending far beyond the visible disk. The universe is not an empty stage with a few bright props. It is a structured place, layered, connected, patiently assembled over immense spans of time. That does not make it less mysterious. It makes it more so. Because now the Milky Way's halo is no longer only the answer to a local question. Why do stars move too fast? Why is the galaxy heavier than it looks? It becomes part of a larger answer to a deeper question. How does the universe build anything at all? And the answer, at least in the current picture, seems to be this. First, gravity gathers hidden matter. Then ordinary matter falls in. Then stars ignite. Then galaxies form. Then groups and filaments emerge more clearly. Then the cosmic web, mostly invisible, becomes softly outlined by light. In that sequence, the visible universe is almost the afterglow of a darker assembly process. That does not mean the darkness is empty or lifeless. It means it is foundational. And this brings us naturally to the next turn in the story. If the Milky Way lives inside a larger web of dark matter, then dark matter is not just some distant theoretical ingredient in the outskirts of space. It may be all around us, here in our own region of the galaxy, passing silently through the solar system, through the Earth, perhaps even through your own body in this quiet moment now. That possibility is both eerie and calming, because it takes the hidden architecture of the cosmos and makes it local again. Not just the structure around the galaxy, not just the web between galaxies, but the invisible presence surrounding us, here, where we already are. Part 9. Could we be living inside dark matter right now? By this point in the journey, the Milky Way has already become much stranger than it first appeared. What began as a bright spiral galaxy, a graceful river of stars, has slowly widened into something far larger and quieter. A luminous disk nested inside a vast dark halo. A galaxy surrounded by an invisible structure so immense that the familiar Milky Way of starlight now seems almost like the glowing center of a much deeper home. And once that idea settles in, another question arrives almost automatically. If dark matter surrounds the galaxy, then where are we in relation to it? Are we merely looking out toward it from somewhere safe and separate, like observers standing at the edge of a fog bank? Or are we already inside it? The answer, as far as modern astronomy suggests, is not subtle. Yes, we are already inside it, not near it, not approaching it, not watching it from a distance. The Earth, the Sun, the planets, the quiet rooms of human life, all of it appears to exist within the Milky Way's dark matter halo already. The invisible structure shaping our galaxy is not some remote shell far beyond the stars. It extends through the broader galaxy, including our region of space. We live not only in the Milky Way, we live inside the hidden mass of the Milky Way as well. That is one of the most intimate and unsettling ideas in astronomy, not because it is dangerous, but because it is so silent. Dark matter, if it is truly there in the way current science suggests, is not something that announces itself with color or sound. It does not drift past the window in visible clouds. It does not collect on your skin like dust. It does not make the air feel heavier. You do not wake up one morning and sense that the galaxy's invisible mass has entered the room. It is more elusive than that, more ghost-like, more patient. It could be all around us, moving through the world, and leave no ordinary trace at all. There is something almost dreamlike in that thought. For most of life, we trust the visible world. We trust walls, light, shadows, objects, weather, temperature, motion. We trust the things that can be sensed. But dark matter asks us to admit that the world may be structurally immersed in something no human sense was built to notice directly. The galaxy around us may be saturated with an invisible presence that neither glows nor speaks, yet still helps shape everything on a cosmic scale. Of course, when scientists say we are inside dark matter, they do not mean that dark matter behaves like ordinary air or water. It is not a thick substance filling space in the familiar way. The density of dark matter in our part of the galaxy is thought to be extremely low by everyday standards. If you could somehow gather up all the dark matter thought to occupy a space the size of an ordinary room, its mass would be astonishingly tiny. In human terms, almost nothing. So when we say it is all around us, we do not mean the room is crowded with hidden weight. We mean that the Milky Way's gravitational environment includes a diffuse background of dark matter even here in the region of the Sun. That distinction matters, because otherwise the idea becomes easy to misunderstand. Dark matter is important not because it is dense in the ordinary local sense, but because it is spread through enormous volumes of space. Over the scale of the whole galaxy, that adds up to tremendous mass. Locally, though, it remains thin, subtle, and almost completely non-interacting. And that is why you do not feel it. You do not trip over dark matter. You do not breathe it in and cough. You do not watch it cast a shadow on the wall. If the leading ideas are correct, dark matter interacts with ordinary matter mainly through gravity, and perhaps through extremely weak interactions that are so rare they have not yet been clearly observed. It moves through the world almost without friction, through planets, through stars, through bodies, through stone, through oceans, through steel, through silence. That image can be eerie if you let it be. Invisible particles, perhaps billions upon billions of them, passing through you every second without your awareness. A hidden rain of the cosmos flowing through the earth continuously. No sound, no pressure, no warning, no sensation. Just a steady silent passage of something we cannot yet name with full confidence. And yet, if you stay with the thought long enough, it becomes less frightening and more calming. Because dark matter, whatever it is, does not seem hostile. It is not a toxin. It is not a force bent on disruption. It is part of the deep background of the universe. It has been with the Milky Way for as long as the galaxy has existed in anything like its current form. It was there while the sun formed. It was there while the earth cooled. It was there while life emerged from chemistry and oceans and time. It has accompanied every human civilization without ever needing our permission or our awareness. Dark matter, in this sense, is not an intruder. It is part of the hidden environment in which all of ordinary history has unfolded. There is something quietly humbling about that. It means human life does not merely happen under the stars. It happens inside a larger invisible galactic architecture. We often imagine ourselves as creatures of the visible world, and of course we are. But cosmically speaking, we may also be inhabitants of an unseen medium of gravitational structure, one that extends through our galaxy and beyond. This question of local dark matter is not only philosophical, it is also deeply practical for science. Because if dark matter exists here in the solar neighborhood, then in principle it should be possible to detect it directly. Not by photographing it, perhaps, but by building experiments sensitive enough to catch one of its rare interactions with ordinary matter. That hope has inspired some of the most delicate experiments in modern physics. Deep underground, beneath mountains and layers of rock, scientists have built detectors designed to listen for tiny whispers from the dark universe. These laboratories are placed underground because the surface of the Earth is noisy in a cosmic sense. Radiation from space, energetic particles from the sun, and all sorts of ordinary signals constantly move through the upper environment. To search for something as elusive as dark matter, Scientists try to shield their detectors from as much background noise as possible. So they go down into mines, into quiet chambers, into carefully controlled darkness. There is something almost monastic about this. Humanity, curious and restless, descending into silence to wait for a nearly impossible signal from the invisible matter of the galaxy. Some experiments use vats of ultra-pure liquid xenon or argon, watching for the faintest flash or tiny energy deposit that might occur if a dark matter particle collides with an atomic nucleus. Others search for axions using strong magnetic fields and exquisitely tuned instruments. Some look for effects in crystals, superconductors, resonant cavities, or other clever devices designed to catch the smallest imaginable disturbance. The common thread is patience. These machines are not explosive or theatrical. They are quiet listeners. And so far, the great story of direct dark matter detection has largely been a story of disciplined silence. No clear confirmed detection has yet settled the matter. There have been hints, anomalies, brief excitement, but nothing that has closed the case in a way the scientific community fully accepts. For some people, that can sound disappointing. But I think there is another way to feel it. The silence itself is teaching us. It tells us dark matter, if it is made of particles, may be even more elusive than early theories expected. It narrows the possibilities. It deepens the mystery. It forces science to become more creative. And there is another way dark matter could be local without ever becoming dramatic. Even if it passes through the solar system, it may do so in patterns shaped by the Milky Way's halo. Some models suggest that dark matter in our region forms a roughly smooth background. Others allow for subtle clumps, streams, or flows left over from the galaxy's formation history. If the Milky Way absorbed smaller dark matter structures over billions of years, traces of those past mergers might still influence the local distribution today. So even in the hidden matter around us, there may be memory. That is one of the beautiful repetitions in this story. The visible stellar halo preserves traces of ancient collisions. The dark matter halo may do the same in its own invisible way. Streams of stars reveal old mergers in light. Perhaps streams or variations in dark matter reveal old mergers in gravity. The galaxy remembers its past on many levels, not only through stars, but through the deeper matter that held those stars together. Still, for all the scientific subtlety, the emotional center of this part of the story remains simple. Yes, we are living inside dark matter right now. Or at least, inside the galactic region where dark matter appears to be present and dynamically important. That sentence does not change the feeling of the floor beneath your feet. It does not alter the taste of water, the sound of breathing, or the quiet rhythm of a room at night. But it does gently change your sense of where you are. You are not only on Earth, not only in the solar system, not only in the Milky Way. You are inside a hidden galactic structure that extends far beyond the visible stars. And that enlarges home in a way that is difficult to reverse once felt. We tend to think of home in layers. A room, a building, a street, a city, a country, a planet. But astronomy adds stranger layers. A solar system, a galactic arm, a spiral disk, a dark halo, a local group, a cosmic web. With each layer, the familiar world does not disappear. It is simply placed inside a larger and quieter setting. Dark matter is part of one of those deeper settings. Not visible, not intimate in the ordinary sense, but undeniably part of the larger structure in which we exist. There is also a strange tenderness to the fact that something so mysterious can be so close. We often imagine the great mysteries of the universe as remote, hidden in distant quasars or at the edges of the observable cosmos. But dark matter, if current ideas are right, brings one of the biggest mysteries right into our own galactic neighborhood. The hidden mass is not only out there in the grand abstract. It is here, interwoven with the place where the sun orbits, where Earth turns, where life has unfolded. And yet, Closeness does not guarantee understanding. That may be one of the gentlest lessons of all. A thing can surround you completely and still remain unknown. Fish do not begin life by understanding water. Human beings do not begin life understanding gravity. We inhabit realities long before we explain them. In that sense, dark matter fits into a much older pattern. We are living within something that science is still trying to name properly. That is not failure. That is simply the human condition at cosmic scale. Sometimes I think that is why astronomy pairs so naturally with sleep. At night, the visible world softens. Familiar objects lose their sharp boundaries. The mind becomes more comfortable with mystery. And in that gentler state, it becomes easier to accept that we do not need to solve everything immediately to belong inside it. Dark matter can remain mysterious and still be part of home. There is also the question of whether dark matter affects daily life in any practical sense. For the most part, no, not in a way you would notice directly. The Earth is held together by ordinary gravity from ordinary matter. Your body, your house, the tides, the atmosphere, the orbits of the planets, all of these are governed overwhelmingly by the familiar matter and forces we already know. Dark matter's local density is far too low, and its interactions far too weak, to shape the daily mechanics of life in a visible way. Its importance emerges on larger scales. Galaxies, groups, cosmic structure. That is an important point because it keeps the mystery in proper proportion. Dark matter is not lurking in your room as a hidden danger. It is part of the larger galactic background. It matters immensely for the Milky Way as a whole, but it does not make the ordinary world unstable or uncanny in a practical sense. The hidden halo can be real without becoming ominous. And still, there is something quietly astonishing in the fact that your own body may be moving through a stream of unknown cosmic matter at every moment. We spend so much of life assuming that what matters most is what presses directly on the senses. But dark matter invites another possibility. Some realities are foundational precisely because they remain in the background. They do not dominate local feeling. They shape larger context. In that way, dark matter is almost the opposite of spectacle. It does not ask for attention. It does not reveal itself through fireworks. It is one of the universe's great patient presences, a hidden contributor to form and motion, a quiet partner in galactic structure. The Milky Way would not look the same without it, might not exist in the same form without it, and yet it proceeds without display. There is a philosophical beauty there. The unseen can be essential. The silent can be structural. The background can be what holds everything together. Perhaps that is why the idea of living inside dark matter feels, after the first surprise, almost soothing. It reminds us that reality does not have to announce itself loudly to be real. Not everything important shines. If these calm journeys through the universe help you drift into rest, you can leave a like, subscribe, or gently share where you're listening from tonight. It is always comforting to imagine many quiet listeners spread across the earth, all resting together inside the same hidden galaxy. There is one more subtle thought worth lingering with before we move on. If dark matter surrounds us here, and if its identity remains unknown, then our own location in the cosmos is more mysterious than people once believed. The old picture of home was simpler. A planet around a star in a galaxy of stars. Already grand, already beautiful, but still mostly made of things that at least belong to the visible family of matter. The newer picture is stranger. A planet around a star in a bright disk embedded inside a massive invisible halo whose substance remains uncertain. We have not left home behind. Home has simply become more profound. And maybe that is the real gift of this question. Could we be living inside dark matter right now? Yes. But the point is not only that the answer is yes. The point is what that yes does to the imagination. It tells us that the mystery of the Milky Way is not merely at the edge of some distant halo. It is woven into the place where we already are. It tells us that the galaxy is not just a visible structure overhead, but an invisible architecture surrounding us now. It tells us that we are not waiting at the threshold of the unknown. In some deep sense, we have always been inside it. And that leads naturally to the final step in the story. Because once you understand that the visible Milky Way is only a bright inner region, and that the galaxy's true body extends far into darkness, and that we ourselves live inside that hidden structure already, the question shifts one last time. The halo is no longer just a scientific object. It becomes part of our address, a new way of defining home. Not merely the stars we can see, but the invisible giant that contains them. And in that final perspective, the Milky Way becomes something even more haunting and beautiful than a spiral galaxy. It becomes a quiet structure of light held inside darkness, a visible memory floating in a vast unseen body, a place where the universe reminds us, with extraordinary calm, that the deepest truths are often the least visible ones. Part 10. The quiet structure of the universe. In the end, the Milky Way becomes more beautiful, not less, when it grows stranger. At the beginning of this journey, it was easy to picture our galaxy as a great river of stars, a bright spiral city in space, a place made of glowing arms, dust lanes, clusters, and a crowded central heart. That image is still true, in the way a shoreline is true when you first stand beside the sea. But now, after following the clues outward, that first picture feels almost like an introduction rather than the full story. The visible Milky Way is real, but it is not the whole body. It is the lit inner region of something far larger, far heavier, and far more mysterious than human beings once imagined. The galaxy we see is only the bright surface. The galaxy we live in is deeper than light. And perhaps that is one of the gentlest revelations astronomy can offer. The universe is not only made of what shines. Some of its most important structures are quiet. They do not sparkle in telescope images. They do not stretch dramatically across the night sky for the naked eye to admire. They reveal themselves through patience, through motion, through gravity, through the way other things behave when held inside them. Dark matter, whatever it ultimately turns out to be, belongs to that quieter category of truth. It does not arrive with fanfare. It does not ask to be believed because it is visually impressive. It simply continues to leave the same signature again and again, in the motions of stars, in the orbits of dwarf galaxies, in the stretched ribbons of stellar streams, in the shape of halos, in the way galaxies gather into larger structures, in the way the universe built itself over time. And the Milky Way, our own home, appears to be one more expression of that same hidden architecture. If you look up on a dark night and see the pale band of the Milky Way crossing the sky, what you are really seeing is a small luminous testimony to something much larger. Not the whole galaxy, but the visible part of it. Not the full body, but the bright evidence that a much deeper body exists. A visible memory floating inside an invisible giant. There is something deeply peaceful in that thought. Not because it makes the universe simple. It does not. If anything, it makes the universe even more mysterious. But it also makes it feel layered in a way that is strangely calming. The stars are not scattered randomly in emptiness. The galaxy is not merely a loose collection of lights drifting without support. The Milky Way is held. It is structured. It is surrounded and shaped by something vast and mostly unseen. There is order here, even if it is not obvious at first glance. We often think of knowledge as the process of making things clearer, brighter, more visible. But sometimes knowledge works the other way. Sometimes it teaches us to respect what cannot be seen directly. It teaches us that light is not always the deepest guide. In the case of the Milky Way, light gave us the first map, but gravity gave us the larger truth. And that larger truth changes what home means. For most of human history, home was Earth. Then home became the solar system. Then it became the Milky Way. But even that expansion now seems incomplete. Because the Milky Way is not merely a starry disk overhead. It is a galaxy embedded in a halo. A visible structure held within an invisible one. A bright local neighborhood inside a much greater gravitational domain. So home, if we choose to define it honestly, is not only the stars we can see. It is also the hidden matter that binds those stars into a larger whole. There is a quiet humility in that. We are creatures of ordinary matter, built from atoms forged in ancient stars, living on a rocky planet around an ordinary yellow star in a minor arm of a spiral galaxy. Already that was enough to make human life feel both precious and small. But now there is another layer. That whole familiar arrangement exists inside a much larger unseen environment, one that has been there all along, guiding the structure of the galaxy without ever becoming part of ordinary sight. And that tells us something about reality itself. Reality is not arranged for convenience. It does not guarantee that the most important things will be obvious. It does not promise that what matters most will be brightly lit. Sometimes the deepest framework of a thing is the part that remains hidden while the visible parts play at the surface. A house is more than the paint on its walls. A tree is more than the leaves catching light. A galaxy is more than its shining stars. The dark matter halo is the Milky Way's reminder of that principle. It says, in the quietest possible voice, that structure can exist without spectacle. That the unseen can be essential. That something can define the shape of home without ever appearing in the ordinary sense as part of the scenery. And if that sounds abstract, perhaps it is only because the scale is so large. If this same principle appeared in a smaller setting, we would recognize it immediately. We already know that visible life depends on hidden systems. Roots beneath the soil, foundations beneath a building, the unseen circulation of air, the invisible force of gravity itself. Dark matter simply extends that pattern to a galactic scale. It is not necessarily a mystical exception. It is another version of a very old truth. What supports a thing is not always what first catches the eye. There is also a kind of emotional maturity in the halo story. At first, it feels almost disappointing to learn that the beautiful bright Milky Way is not the whole galaxy. But that feeling passes. Because what replaces it is not disenchantment. It is depth. The visible galaxy does not become less meaningful because it is incomplete. It becomes more meaningful because it is now understood as part of something larger. The spiral arms, the bulge, the disk, the glowing band in the sky, all of it becomes richer when placed inside the halo that contains and shapes it. The Milky Way was beautiful as a visible object. It becomes hauntingly beautiful as a visible fraction. And perhaps that is why dark matter has such power over the imagination. It is not just a scientific problem. It is a change in perspective. It takes something we thought we knew, our own galaxy, and reveals that it has always possessed an invisible dimension. It tells us that the familiar world above us, for all its grandeur, is still only part of the story. That is not a disappointment. That is the universe continuing to exceed us. And it is doing so in a very particular style. Not with violent novelty. Not with fireworks. But with a patient unveiling. A soft correction to human intuition. A reminder that truth often lives just beyond the boundary of what first seems complete. The Milky Way's dark matter halo also changes the meaning of loneliness in the cosmos. When galaxies were imagined primarily as bright islands in a dark sea, intergalactic space felt almost terminally empty. But halos complicate that feeling. They suggest that galaxies are not only points of light but extended territories of gravitational presence. And once you widen further into the local group, and further still into the cosmic web, the universe begins to look less like isolated lanterns in a void and more like a connected architecture outlined by starlight. Not crowded in any ordinary way. Not intimate in the human sense. But structured, related, layered. That matters, emotionally, more than it may first seem to. Because one of the quiet fears hidden inside cosmic thinking is the fear of emptiness. A fear that beyond the visible lies only blankness. But the halo offers another possibility. Beyond the visible lies structure. Beyond the bright edge lies a deeper body. Beyond the stars lies a hidden framework. The universe is not less than it appears. It is more. And yet, for all this expansion of scale, the final feeling of the halo need not be cold or alien. In fact, it can be surprisingly tender. Because the halo has been with us the whole time. It was there long before human beings asked what a galaxy was. It was there while early life stirred in Earth's oceans. It was there while stars formed and died, while continents drifted, while languages emerged, while civilizations rose and fell. The Milky Way's invisible structure is not a new arrival in the story of home. It is one of the oldest parts of that story. We are only now becoming conscious of it. That is one of the most touching patterns in science. The universe often contains realities long before human beings learn their names. Gravity was here before Newton. Microbes were here before microscopes. The expansion of the universe was happening before we noticed the galaxies receding. And the dark halo of the Milky Way was holding our galaxy together long before anyone understood that the visible stars were not enough. So perhaps the real change is not in the galaxy, but in us. We are the ones widening. We are the ones learning that home is larger than the old maps suggested. We are the ones discovering that the night sky, beautiful as it always was, is also the doorway into a deeper unseen structure. And maybe that is why astronomy pairs so naturally with stillness. It invites a wider kind of breathing, a wider kind of belonging. It takes the little bright dramas of daily life and places them gently inside a larger frame, not to erase them, but to soften them, to remind us that reality has depth, that time has patience, and that existence is carried inside structures older and calmer than our own brief concerns. The Milky Way has been moving through darkness for billions of years. Its stars have orbited within the halo through spans of time too large to feel directly. The sun has gone around the galaxy again and again, carrying Earth and all its future life with it. And all the while, the hidden mass has remained quiet, unseen, structurally faithful. A vast presence making the galaxy more stable, more coherent, more fully itself than starlight alone could manage. There is almost something gentle in that constancy. And if the identity of dark matter remains unsolved, that does not diminish the beauty of the story. In a way, it completes it. Because the universe has not merely offered us a finished answer to admire. It has left us with an open door, a genuine mystery. One of the rare kinds of mystery that grows deeper, not shallower, as more is learned. We know enough now to understand that the halo is real in its effects, real in its scale, real in its importance. But we do not yet know exactly what this hidden matter is. So the story ends, for now, with both understanding and wonder held together. That is a lovely combination. Too much certainty can flatten the cosmos into a set of solved diagrams. Too little knowledge leaves only confusion. But here, in the case of the Milky Way's halo, we have the more beautiful middle condition. We can see enough to understand the outline, enough to know that our galaxy is far larger and stranger than it appears, enough to realize that the visible stars are only the bright core of a deeper body, and yet enough remains unresolved that the universe keeps its mystery intact. That is not a flaw. That is one of the reasons science stays alive. And perhaps it is also one of the reasons this subject feels so restful in the quiet hours. The halo does not demand that we solve it tonight. It only asks us to feel its scale, to understand its role, and to let the idea of an invisible home settle gently into the mind. A galaxy made of more than light. A home defined by more than what can be seen. A structure whose deepest truth is carried in darkness. If these calm explorations help you unwind, you can quietly leave a like, subscribe, or share where you're listening from tonight. It is always comforting to imagine listeners in many different places on Earth, all resting together inside the same hidden galaxy. And maybe that is the right place to end. Not with a dramatic answer, but with a softened vision of what the Milky Way really is. It is still the pale band across the sky, still the spiral galaxy with arms and dust and a crowded heart, still the home of our sun, our planet, and every ancestor who ever looked upward and wondered. But it is also more than that. It is a luminous center inside a vast dark halo. It is a visible city inside an invisible country. It is a bright memory carried within a deeper mass. It is a quiet structure of the universe, where light floats inside darkness and remains held there. When you next imagine the Milky Way, perhaps do not picture only the stars. Picture also the enormous unseen halo surrounding them. Picture the visible disk nested inside a much larger body. Picture our solar system traveling through that hidden realm without ever noticing it directly. Picture the galaxy not as a simple island of light, but as a layered home, partly visible, mostly mysterious, and wonderfully larger than it first appears. And if the night feels a little calmer after that, perhaps it is because the galaxy itself is calm on its deepest level. A vast invisible structure. A patient gravitational home. A place where the universe, without noise or urgency, reminds us that the deepest architecture of reality is often the quietest. And somewhere inside that invisible giant, on a small planet circling one ordinary star, here we are, still wondering, still learning, still home.